And what we particularly spoke about was geostationary. First of all, the geostationary orbit satellite. You must remember the three conditions for geostationary. There are three conditions for a satellite to be geostationary. First condition is that the height of the satellite above the Earth is about 35,800 kilometers.
That's minimum, though.
No, exact. Can't be more, can't be less. What happens if it's any more than that? What happens if the satellite is further away than 35,800?
The gravity. Go space.
Yes, it either goes into space or it rotates at a different speed than the Earth. And if it rotates at a different speed than the Earth, it is not geostationary, is it?
Out of the orbit.
Yes, probably it will fly off. If it's less than 35,800, two things can happen. Either it will fall to ground, or it will rotate again at a different speed, and it's no longer geostationary. So there is only one position, shall we say, from the Earth that the satellite will be in geostationary orbit, and that is 35,000 kilometers. 35,800 is probably more precise than that, but 35,800 kilometers above the Earth. Also, to be geostationary, two other conditions. It must rotate at the same speed as the Earth. Okay? Once every 24 hours. And it also must rotate around the equator. Because the Earth, if this was the pole here, the Earth is rotating this way, the satellite must rotate the same, mustn't it? It's no use the satellite going that way.
Yes.
All right? Because it's not going to be stationary with respect to the Earth. So there are three conditions. These two are linked. If I was to change the speed of rotation, or whoever puts it up, changes the speed of rotation, then that distance will change for it to remain in orbit. Basically, anything in orbit around, because of the gravity of the Earth, the speed and the distance are related. Now we want the speed to be 24 hours rotation, so the distance has to be 35,800. You can't have one without the other. If you were to therefore look at the Earth, assuming we were looking at the Earth from a different point of view, say this was the pole in the middle here. In other words, we were looking down on top of the North Pole, then the satellite is rotating here, isn't it? Do you agree? Around the equator. It means that all geostationary orbit satellites, all of them, are in the same line. Right? And there are quite a few of them up there now. But there's, I don't know how many satellites altogether, but they must all be rotating in exactly the same
If
line.
the satellite in the same orbit?
Yeah, all geostationary satellites.
Geo stands for what?
Geo means the Earth. Geo for geography. Geo meaning the Earth. Stationary with respect to the Earth. It's not stationary absolute, is it? I mean, it's rotating. But with respect to the Earth, if somebody's standing on the Earth, that satellite will always be in the same position in the sky, no matter what time of day or night.
Okay, there is no any, it's not a must to stay at 35,800 kilometers to have the same time to rotate.
It is a must, yes.
Why is it?
Because if it rotates any faster, okay.
Not about rotating it. What's controlling the speed, first of all? Is it...
Well, when it's launched,
Yeah.
okay. I mean, technically, I'm not quite sure the mathematics involved, but when it's launched and the rocket deposits it at a certain distance, whatever distance it deposits it, that determines the speed at which it will rotate. Okay? That will determine the speed at which it will rotate. Because it forms a natural balance. If it rotates any faster, remember yesterday I was speaking about centrifugal force.
Yeah.
If you rotate any faster, the force on the satellite, doesn't matter how heavy it is, the force on it will be to move further out.
Yeah.
Okay? If it rotates any slower, it will move further in because of the gravity. You see, one balances the other. Now, the question is, gravity's fixed, okay, but gets less and less and less as you move further and further away from the Earth. However, one thing we do have control of is the outward force, and the outward force is the speed at which it rotates. Now, we want the speed to be fixed at once every 24 hours. We want that to be fixed. Okay? So therefore, we're fixing the outward force. Do you agree with that? If you fix the speed, you fix the outward force. So it will go out until it matches the gravity. Okay? When it matches the gravity, then it will stay in that position. And it just so happens that the gravity, the force of gravity on that satellite to match the outward force will be right at 35,800 kilometers. That's what they're saying. And then it's balanced. So if it rotates at once every 24 hours, you must be that distance. One leads to the other. Actually, it's not just for satellite. Any orbiting object has the same constraint, exactly the same. And it doesn't really depend on the actual weight of the satellite. A heavier satellite doesn't have a different distance or anything like that. One balances the other. This is how they calculate distances from planets of different moons. Like our moon is such a distance away from our planet. That distance, okay, is related to the speed at which the moon rotates around the planet. One is related to the other. It's a balance between the two. Now, geostationary orbit satellites then are quite a long distance away from the Earth. They're the furthest satellites. But they have one advantage, of course, and that is they are geostationary. So they're only going to be in a fixed position relative to the ground. As the Earth rotates, the satellite rotates. So it always appears in the same position. This is an advantage because the type of antenna that is used to communicate with those satellites is a directional antenna. Now we're going to talk a little more about antennas later. But a directional antenna is one that doesn't radiate or doesn't receive from all directions, but basically from one direction. Now you all are familiar with the look of the dish antenna, right? Okay. That's a directional antenna. You point it towards the transmitter or receiver. Well, if you're the receiver, you point it towards the transmitter. Now, of course, if we're going to use this type of antenna with a satellite communication, then much better that the satellite's geostationary, because you can then point it to the one position and leave it. But if that satellite was not geostationary, then it's going to move with respect to the Earth, isn't it? In other words, as time goes on, the satellite will actually move across the sky, which means you have to move your antenna to track it, to keep on track. Not a very good idea. So all, for example, long-distance communication satellites, most long-distance communication satellites will use geostationary satellites. All TV broadcasts are using geostationary satellites because when you erect one of these things, you don't want to have to move it all the time. It's got to be fixed in that position. When you install the antenna, depending on which satellite you're going to use for your communication, you fix it pointing to that position. And then that's it. It should remain. There was a Russian satellite that was put up some years ago, and unfortunately it started to wobble. And it produced like a little figure of 8 wobble. It was rotating, it was geostationary basically, but it was moving a little bit over a period of a day. So sometimes it went in, sometimes it went out, sometimes you received it, sometimes you didn't. It can be quite critical, you know, to the nearest degree, because we're talking about long distances here. Now, how the satellite works, all satellites work on pretty much the same principle. Basically, you can think of a satellite as being a repeater or regenerator of signals in its simplest form. So what happens is you have a ground station somewhere where you will site your transmitter, and it will have an antenna which will beam a signal to the satellite. The satellite receives the signal, amplifies it perhaps, regenerates it more likely if it's a digital satellite. Remember, the older types were analog, weren't they? Newer types of signaling are digital. So let's say it regenerates the signal and then retransmits the signal back down to ground. Now, most geostationary satellites, in fact most satellites, have also a dish-type antenna which can position the receiving beam to a small area of the ground, not necessarily the whole of the Earth. So, for instance, let me draw a simplified diagram here. If I have, I'll draw it a bit closer so we're not just a little bit out of scale. If this is the Earth, then the satellite's down beam won't cover the whole of the Earth necessarily, because remember, the power from the satellite, the power for the signal comes from the sun, doesn't it? It's using solar cells. So we're not talking about a lot of power here. So what it does normally, it beams to a relatively narrow beam to cover the Earth. Remember that most of the Earth anyway is water, isn't it? It's the sea. Well, for a lot of satellites, particularly for TV broadcasts, they want it over the land. So they don't want to waste power. So they have what they call a footprint. This is what they call it. Which means a certain area of the ground will be covered by a particular transmission from the satellite. Now, a satellite can have more than one footprint. For instance, the Orbit TV satellite has two footprints, an eastern and a western. They actually overlap a little bit. What they call beams, an east beam and a west beam. And they have different frequencies as well, so they don't interfere where they cross over. And you can receive either this or this, depending on whereabouts you are on the globe. One thing to remember, of course, is that any given satellite, just one satellite, cannot cover the whole of the Earth. That's impossible. Because, of course, because if you think about it, the way the satellite, even if it beamed everything it could, it's only going to cover one side. Yeah, and to get real good coverage, you would need, if you wanted worldwide coverage, you would really need 3 satellites. Like this. If you imagine this is the Earth, you have 3 satellites, one covering this side, one covering this side, one covering this side. Well, actually, I'm a little bit wrong, like that. See, to make sure you get full coverage of the Earth. That's the only way you could do it. So any one satellite cannot cover the whole of the globe. So satellites are going to be used depending on where they're placed. So that's a geostationary satellite, okay? Used for TV broadcasts and, to a certain extent, for long-distance backbone communication, particularly on the internet. It can also be used for telephone channels. Now, I mentioned yesterday the sort of frequency bands that we would use for satellite communication. What frequencies would you use for satellite communication? Okay, we're talking about gigahertz here, aren't we? So approximately 3 gig to about 30 gig. We said that this was in the microwave area of bands. They call it microwave. This is a loose term, it's not an exact term. The wavelengths are very short, aren't they? Very short. 3 giga, for instance, is only 10 centimeters, isn't it? Isn't that right? 10 centimeters. And 30 gigahertz, of course, is
1 centimeter.
1 centimeter. So we're talking about wavelengths of about this big. In fact, this is the reason why we can use dishes, because of such short wavelengths. And of course, one advantage of using these frequencies is you've got a lot of bandwidth, a wide bandwidth. Imagine how many telephone channels you can fit in if you were using frequency division multiplexing. How many telephone channels you can fit in there? It'd be thousands and thousands of telephone channels. Okay. However, there is one disadvantage with using the geostationary satellite for telephone calls. One big disadvantage, actually. And that is time. I want to talk about the time it takes a radio wave to get from the transmitter to the satellite. Now, how fast does the radio wave travel?
3 times 10 to the power 8.
Yes, 3 times 10 to the power 8 meters per second, isn't it?
Yeah.
Okay, now look how far away the satellite is. It's over 35,000 kilometers away. Even if it was, say, 30,000 kilometers, 30,000 to make the figure simple, how many meters is that?
35 million.
Yes, 35 million meters. Well, let's say 30 million meters to make the figures simple, so we're not dealing with a lot of mathematics here. Even at 30 million meters, okay, that's 3 times 10 to the 7th, isn't it? Meters. Do you agree with that?
Yes.
In other words, this distance is over 3 times 10 to the 7 meters. Right? Now, let's consider how long it takes a signal to get from the transmitter to the satellite. How much time it takes.
10 seconds.
Yeah, if you, no, if you take it as the distance, right, is this, right, divided by the speed.
The distances will be double.
Yeah, but let's just do the one uplink. We call this the uplink, by the way. I think that should be pretty obvious. And this we call the downlink. I'll put those words in because I remember they're mentioned in the book. Just considering the uplink time for a moment, the time it takes is going to equal the distance divided by the speed. Is that right?
Yes.
Now the distance is 3 times 10 to the 7th, and the speed is 3 times 10 to the 8th,
Yes.
isn't it? Which equals 0.1. Do you agree with that?
Yes.
Seconds, approximately. Well, this is exact, but I mean, you know, this is going to be approximate. So 0.1 second for the radio wave to get from transmitter to satellite. Now, of course, the satellite's got to regenerate and then retransmit that radio wave back down to the ground again. Now, assuming it does that instantly, but it won't do it instantly, it'll take a little time itself, but if we just ignore that time, the time it takes to get from the satellite back to the ground will be the same as this time.
0.2 seconds.
Another 0.1 second. So that will mean a total transmit-receive time, a turnaround of 0.2 seconds. Right?
Yes.
So the time for transmitter and receive of signal will be approximately 0.2 seconds. A fifth of a second. Fifth of a second. Now, right, the question is this important? Well, the answer is it depends how we're going to use our satellite. If we're going to use our satellite for TV broadcast, where we're receiving a TV signal, then I don't think it's going to be very important at all. So we're receiving it 1/5 of a second later than it's sent, so what? No big deal, I don't think. And if it forms the backbone of a communication system, such as would be used by the internet or indeed any computer-to-computer communication, again, no big deal. Fifth of a second is nothing compared to what you might normally need to wait for a download. But, and this is the big but, what if we're going to use this satellite for telephone calls? Now, a fifth of a second might not sound very long to you, but if you're talking to somebody and it takes a fifth of a second for your voice to reach them and another fifth of a second for their voice to reach you, right, the delay, it is difficult to have a conversation.
Cost more money.
Well, it's like the echo without the sound.
Yeah.
The point is, you know, when you're speaking to somebody, if there's a delay, they start to speak before you finish because they think you've finished or they think you're saying something else. It's very difficult to have a conversation, and it's only a short period of time. But you know, the way we use conversation, the way we're used to using conversation. You know, if I'm saying something and you want to interrupt me, you just say, and I'll stop immediately. But of course, in a telephone call, that takes 2/5 of a second, you know, for the turnaround time, because it takes a fifth of a second for my voice to reach you, and another fifth of a second for your voice to come back to me.
Yeah.
Then it's difficult to have a telephone conversation.
We saw that on TV in the live.
Yes, you see this on, like if you're watching a news broadcast,
Yes.
and they transfer to somebody else in a different part of the world. There's a delay before they realise they've got to speak.
Sometimes the picture faster than
The picture's maybe faster than but anyway, the point is that sometimes, like if they go over to another reporter or something, by the time that reporter says anything, it's a delay. And it's because they're communicating by geostationary satellite. So, unfortunately, it can handle telephone calls, but they're not very good. Right. So if you make a long-distance telephone call, right, strictly speaking, your telephone company should connect you by landline, in other words, or by low-orbit satellite. That's what they should use. I'll talk about those in a minute. That's the normal way. But if they're really short of bandwidth, in other words, they're short of lines, telephone lines, trunk lines, they will use some of the geostationary. But they should charge you less for it. They won't, of course, but they should. And you can always tell when you're on a telephone call to somebody, if they're using geostationary, it's very cheap for them, geostationary, because of the large number of channels you can fit in the thing. But it's not really good for the user. And I think nowadays they're using it less and less because of it. It's not a good idea. It's okay for TV, it's okay for computer-to-computer communication, no problem with that. But for human communication, it is not a good idea. It is not, well, it's difficult to have a conversation.
There is some mobile for direct to satellite.
Yes, but not for geostationary. Not for geostationary. So, although we're talking about the geostationary satellites, they have certain uses. They're on their own, though. They're special, right? Certain uses. The use would be TV broadcasts. The use would be computer-to-computer communication, so they could form part of a backbone of a computer system, such as the internet.
What about aircraft?
Aircraft would probably use the low-orbit satellites, I would think.
Aircraft is moving. How they control it?
Well, that's right, you see. I mean, aircraft's moving anyway, isn't it?
Yeah.
So there's no advantage in using geostationary. If the aircraft's moving anyway, there's no advantage in using a geostationary.
Using fax and telephone.
Yes, that's right. So they wouldn't use geostationary satellite.
No, I believe that his question is, what if an aircraft interrupts the...
Oh, interrupts. Was that your question?
Yes.
Okay, well, it depends on what it's interrupting. If it's interrupting the uplink or the downlink. The aircraft, the distance that the aircraft will fly from the Earth is what? What's the cruising altitude of, say, 747?
35,000
About
feet.
35,000 feet, right?
Divided by 3.1.
Yeah, so you're talking about 10,000 meters approximately. 10,000 meters. So if we say that's 35,000 meters, this is 35,000 kilometers. This is 35 million meters. Right, 35,000 kilometers. 10,000 meters is here. That's where your aircraft is, above the ground. You know, very, very close to the ground compared to your satellite. So as far as these up and down, particularly the downlink covers a very wide area. The aircraft's not going to make any difference. It's like a fly flying in front of a light quite some distance away. You're not going to notice it. Right? Is that the question you asked?
Yes, what about the antenna of aircraft?
No, I thought that was your question. Is the aircraft receiving a signal from an yes? The aircraft would not use the geostationary necessarily. It would probably use one of the low orbit satellites, which I haven't spoken about yet, but I will mention. Probably.
Is there any communication between one satellite and another?
That's an interesting point. There is actually, but not, now I'll come to mention it. I'm not quite sure the answer to that regarding geostationary. There could be. Certainly there is when it comes to low-level satellites, low-level orbit satellites. Quite sure. Remember, there's 3 satellites required in geostationary to cover the whole of the globe. Where you have a transmitter here which needs to send a signal that's going to be broadcast throughout the whole of the Earth, right? The whole of the globe, whole of the world. So you might say, okay, well, he sends a signal up to this satellite, and then this satellite will retransmit it on its downlink. But then you could say this satellite could also retransmit it to the next satellite, which can transmit its downlink, and this one transmit to the next satellite, which transmits its downlink. That is possible, but whether that is done, I don't know. I don't know the answer to that. When we talk about low-level orbits later, that's certainly the case. They do that. But for the geostationary, I really don't know if that's the answer. I'm not sure. But certainly possible, yes. Possible to do that.
But the delay will be more.
Indeed it will, yes. Again, not very good for telephones. Okay for other communication, but not for human telephone
The new
conversation.
aircraft, there is some troubles with the satellite.
No, there's bound to be, yes. But I'm not so sure that aircraft use the geostationary. I don't think they use geostationary satellites.
But there is another kind of satellite.
Yes. This is only geostationary we've talked about so far.
How many kinds of satellite?
Well, we're only going to talk about 2 types. Geostationary and what we call low orbit. Actually, to be technical, there are in-between types as well, but I'm not going to, you know, we haven't got time to do every possible type.
I thought it is only one kind.
No, there isn't. You see, you've got to be careful. If ever you talk about TV broadcasts or what they call the backbone communication system, computer-computer, as used on the internet, then it's geostationary for sure. Occasionally, it can be used for telephone calls, but not very good. It's not a good media for telephone calls because of the delay, because of that. For those sort of things, we need low orbiting satellites, which I'll talk about.
Anything below the low orbit satellites?
Well, they do actually split it into groups, I think, but I'm just going to talk about them in general as low orbit satellites. When I say low orbit, of course, they're still way above where an aircraft would fly.
Yeah.
You know, way above that. I mentioned yesterday the shuttle. People never heard of the shuttle? The space shuttle?
Yes.
You know, from NASA? this thing here, which looks like an aircraft when it goes into space. Discovery and all that, Challenger. Now the space shuttle goes into space, but it only goes about this distance. It goes nowhere near as high as a geostationary satellite. Can never reach it. So one thing about, sorry? I don't know, technical reasons. There are technical reasons for it. It could be something to do with their orbiting.
But they carry satellites.
But sorry?
They carry the satellites.
They put into orbit satellites, don't they? But their satellites are all low orbit satellites. They cannot put into orbit directly the geostationary satellite. They have to be put in through rockets only, unmanned. That's another reason why geostationary satellites are very expensive. If a low orbit satellite breaks, then you can send a shuttle up to fix it, perhaps. But if this breaks, say goodbye, yes. Say goodbye to several hundred millions or even thousands of millions, I don't know. Certainly hundreds of millions of dollars. So they have to be very, very reliable. There's a lot of backup circuits, of course. I mean, they're not just going to rely on one particular circuit to do a job. There'll be a backup that they can switch in. And the way they're designed is quite complex. And reliability is very important. All the contacts and the conductors will be made of the very best materials, gold and silver, not just copper, to get extra reliability. Yes, that's true. Very expensive to put into orbit, but once they're up there, they can earn the money through charging for bandwidth. So many reals per kilohertz of bandwidth, and they've got hundreds of thousands of kilohertz to play with. So they can make the money. That's the only way they can make the money, of course, for doing that. Quality point of view is the fact that if you get somebody who doesn't like you, they could send a rocket up and blow your satellite up.
Star Wars.
A bit like Star Wars. And you've lost your communication. So you can't rely on the satellite. You know, the military would never rely on that. No, they won't rely on that. Or any satellite. They want a backup. They want something they can control directly, such as cables underground and things like that. Or local microwave point-to-point or something, more control of. But I mean, if all this is doing is just TV broadcast, then nobody's going to bother, I suppose. That's the idea. So that's geostationary. Geostationary satellite. Who would what?
Did anyone do this?
HF and then SHF. Line of sight communication. I know it sounds strange to talk about looking at a satellite, but what we're talking about, in theory, you can. If you had a very powerful telescope, you should be able to see the satellite. In practice, radio waves are the best way to see your satellite, but it is line of sight. It must be direct, point to point. Again, if you have a dish antenna, say, to receive your satellite, if somebody's in front of that, you lose your signal. If anybody's got a dish antenna and a bird lands here on the, which is not unusual, just you lose those bits. That's like impulse noise, only it lasts a little bit longer than a few microseconds, and you lose your bits, you lose your signal.
Sometimes, the dish, it is broken, and it is not
broken, yes.
It is not affected.
It does affect, yes. It means it's not as good. Yeah.
So that is to make it focus.
It is. It's like focusing a light beam, actually. We'll talk about antennas later. We'll talk a little more about antennas. We're not going to go too deep. Technically, you can spend months talking about antennas. People specialize their whole life, work on antennas. We're only going to go through it roughly. Okay, so that's geostationary, fixed in relation to the ground, in relation to the Earth. Now let's talk about a different type of satellite, which I'm going to loosely call low orbit, meaning they're not as far as this at 35,000, they're much closer to the Earth. And we'll see the advantages and disadvantages and all the rest of it. If you go to the airport and you look over, actually it might be an idea for us to take a trip down there sometime.
Tomorrow.
Yeah, either this week or next week. So you'll notice that there are some antennas at the airport, and there's some buildings, and then next to the buildings you have some masts, thin masts like this. And on top of the mast you have some antennas which, if you look at them from the top, they look something like this. I don't know if you've ever noticed these.
Like the Royal?
In the Royal, yeah, they're part of the Royal Comms antennas. They're actually log periodic antennas. These, actually there's two types, there's a YAG and a log periodic, but what I really want you to observe on the antennas is the lengths, right, of these outstruts here. These are actually individual dipoles, right? That's right. Don't forget, in HF they need to cover a wide range of frequencies, don't they? To maintain communication to a certain distance. So the antennas are quite complex. The antennas that they use there, they're built so as to handle a wide range of frequencies. And in its simplest form, the easiest way to think of the way the antenna works is to think of them as a number of dipoles, each of a different length, right? But they're all connected to the same transmitter. We don't switch between these, they're all connected, and it produces what is called a broadband antenna, an antenna which is efficient at any frequency within the HF band. Okay? So each one of these can be considered an individual dipole, and they're all connected together to the one transmitter source. So that would be used for HF communications as a good example.
Excuse me?
Yes.
For the dipole, is it placed horizontally or vertically?
A very good point, and that's the next little thing I'm going to talk about, actually. And it's an interesting point and an important point, whether you place it horizontally or vertically. Remember what we said about the way our antenna works. We have essentially magnetic fields around the conductor, don't we?
Yes.
Right, that way round. And our electric fields from end to end of the conductor. Now if if you were sort of stood in front of the antenna and you could imagine these fields radiating towards you, what you would see would be like a grid like that. Imagine this is like the skin of a large balloon that's expanding.
The vertical.
That's right.
Would be the electrical.
Exactly. The vertical field would be the electrical field, wouldn't it? In this case. These are electric fields, and these would be the magnetic fields. Do you agree with that? That's right. Now, if you're building an antenna to receive this signal, it works the opposite way. What the antenna does that receives this signal, it's like the secondary of a transformer. Remember, in a transformer, you've got a primary that produces magnetic fields, and a secondary that picks up the magnetic field. Well, if I want to design an antenna to receive this, essentially, a good transmitter antenna works the same way as a receive antenna works the same way as a transmit antenna. I would get a length of conductor, and I would mount it some distance away, whatever it is, from the transmitting antenna, and I would make sure, and I would connect the middle, in this case, to the receiver instead of to a transmitter. But I would have to make sure that that antenna is aligned exactly the same as the transmitter antenna. If I didn't do that, if I put the antenna this way, I will not receive the signal properly, because the electric field is not going to induce a voltage in the length of the antenna, and the magnetic field is not cutting. The magnetic field's got to cut it at right angles, and it isn't going to do that. So if I put my antenna that way, I would, in theory, receive nothing. We call this polarization, and it's an important point. Now, polarization is, in its simplest form, is the direction of the electric field. That's what they chose as the definition. So, it's the direction of the
maximum at the middle.
It is, but when you get some distance away, it doesn't really matter about that, because it's radiating like a balloon anyway. So we can ignore the fact that it is maximum at the middle. But you're right in the sense of the way it was generated. But the definition of polarization is the direction of the electric field, which is the same direction as the antenna itself. So, for example, if I've got an antenna like that, okay, is that going to be horizontally or vertically polarized? Vertically polarized, exactly, because the electric field's between the ends. That's vertically polarized, horizontally polarized. And it's important to make sure that your receiving antenna is the same polarization as your transmitting antenna. If it's different, then you're not going to receive the signal as well. You probably, in theory, you should receive no signal. In practice, you might pick up a little bit, for reasons which we'll talk about in a minute. But essentially, that's what polarization means. And you can either have vertical or horizontal polarization. Let me just erase this. So, for most cases, it's either vertical or horizontal. Vertical or horizontal. Now, in the example of the HF antenna I just gave, using the log periodic, that was really a horizontally polarized antenna, because they're that way.
Which example?
The one I gave for the log periodic at the airport,
Yeah.
weren't they? So that would be an example of a horizontally polarized transmission. However, remember, we use HF communication, it's reflected by the ionosphere, isn't it? By the time it gets to the receiver, things get mixed up a little bit. Because of the distance travelled and the way it propagates, the way it goes up to the ionosphere and is reflected back down again, the polarization ends up a mixture of the two. So it's not too critical. You end up with a complex wave which consists of both horizontal and vertical. So it's not too critical in that case, in that example, as to the way you align your receiving antenna. But it is important when we're considering such things as microwaves or UHF or maybe even VHF. Because the shorter the wavelengths, the more critical the polarization becomes. You might have noticed if you tune your TVs into channel 1 or channel 2, Saudi channel 1 or channel 2, at the beginning, before they start transmission, they give you, first of all, a list of channels, don't they? And they'll tell you whether it's vertical or horizontally polarized, the transmission. That's right. Some are vertical, some are horizontal. Now, why do you think they do this? Why don't they put it all as horizontal or all as vertical?
End of channel.
The distance between.
Well, I haven't said anything about one going a greater distance than the other. As far as we're concerned, they're both the same as far as distance goes. And no, it didn't make any difference that way. No, reduce that interference. To make the interference less, they'll say, okay, we'll make that one vertically polarized, we'll make that one horizontally polarized. Now if you've got a receiving antenna, depending on which station you want to tune into, you would mount your antenna this way if you want to receive this guy, and you would also tune into his channel, of course. But if you want to receive this guy, you tune into this, assuming you're living in the middle here, you've got a choice. You can tune into this guy, but then you would have to mount your antenna physically on the roof or whatever you put it that way. Now this helps to reduce interference between the two. That's the only reason. Apart from that, there's not a lot of difference between using vertical or horizontal polarization.
So to avoid interference?
To avoid interference.
But you just mentioned that after the signal hits the ionosphere,
That's HF. That's HF. This is not HF. This is direct line of sight communication. We're talking about broadcast TV, which uses VHF or UHF. Now, with VHF and UHF, of course, we're not bothered about reflections. It has to be more or less line of sight.
the HF is the only frequency.
Basically, yeah.
Okay.
It's,
we won't use dipole antenna for HF.
Well, yes, they do, as I described here, but it's a very large. You're talking about receiving HF, are you? Transmitting HF. Yes, we do. At the airport, we have these what we call log periodics. They're dipoles.
But omnidirectional.
Remember, a different length for each frequency in the HF band.
But
That was an example of
It's
a.
omnidirectional.
Actually, it's directional. It's not omnidirect, but it's a directional for a different reason because it's using many dipoles.
that reason, please.
When I haven't covered it yet. I'll give you a note on this in a minute.
So the other station maybe should be same antenna to receive it.
Generally speaking, with HF, you can receive it with any antenna. It's not too critical.
Omnidirectional.
Probably. A whip antenna can be used.
so HF and above frequencies can be transmitted on dipole.
Yes, indeed. A dipole is the first antenna I'm talking about, but I haven't really yet talked about different antennas. When I do, you become a little more clear what frequencies are used for which. Theoretically, a dipole can be used at any frequency. The only limit is practical, isn't it? That's all. Space. I mean, if we were talking about very low frequencies, that dipole would have to be hundreds of kilometers long. In theory, yes, but in practice, not something, you would do. That's the only difference. And so really, we've got to think of the practical aspects of the dipole. But if we're talking about, say, microwaves or UHF, then the antennas become reasonable. A dipole's only that big, or maybe only that big. So it's reasonable. It's within reason. We can use it. No big deal.
And it's better since it's the most efficient.
Yes, and since it's the most efficient, indeed it is better. And in fact, we can make it even more better by making it directional, as we'll see later. But because don't forget, this is omnidirectional by itself. But when we get to the lower frequencies, that's when it becomes a problem. That's when our dipole becomes a bit of a problem. Now, the lowest frequencies that we will ever need to be involved with is the HF frequencies. We're not going to go lower than that. In the company, we don't broadcast on, we don't use MF, medium frequencies. We don't use LF. Not many people do. So we're not bothered about those, are we? The lowest we're going to deal with is HF. And that's for the Royal Comms. Even that's only one department. So,
all our station is VHF.
yes, either the VHF, and that's the SMTS, UHF, which is our walkie-talkie system, or microwave. That's basically what we have.
Why do we still use HF?
Well, again, there's a bit of a history to it. When the system was first installed, it was really the only way you could guarantee communication with all your aircraft around the world.
Also
Guaranteed communication. And even now, sorry? Because of use. That's right. We're talking about worldwide communication from Jeddah to any of our aircraft in the world. Okay?
on ground.
On the ground. It can be done in the air as well, basically on the ground, because you know precisely where it is on the ground. Whereas if it's in the air, it's moving, and you might have to change your frequency too often. But all the aircraft's fitted with HF receivers and transmitters. And of course, we've got our HF transmitter receiver at the airport. And the idea was that we don't normally use that, but we've always got it. So if anything goes wrong, and we want to communicate with that aircraft directly, not through an agent, not through the airport or anything, directly with the aircraft, then we can use our HF.
Honest of this.
Well, it's still used. There's two parts to Royal Comms. There's the Royal flights and there's the standard.
No, instead of this,
There's no alternative yet. Otherwise, they would have done that. No, they don't use that. Well, even if they did, they wouldn't rely on it. I mean, they use satellites now to communicate to aircraft, of course. But they still use the HF just in case. That belongs to Saudi, run by Saudi, no other countries involved. We're not relying on somebody else's satellite. Because one thing about a satellite, whoever owns the satellite can switch it off at any time. Right? This is very true about GSM. You know the not GSM, the global positioning, GPS. You know the global positioning things you can get, tells you where you are. That runs by satellites.
we have one of them.
Yeah. You can buy them now quite cheap. But those satellites are owned and run by the US military. And they can switch them off like that. Whenever they want. Huh? So they're nice, but they've got total control. And it's the same with communication satellites. Yes, we can communicate, and we do communicate, mainly by satellite to our aircraft. Why not? It's there. Why not use it? Just like our GSM phones. But if somebody wants to switch those satellites off, we have got our HF communication to fall back on.
Realistic. If someone wants to switch it off, they can also broadcast the HF frequency to...
They can, yes, yes. But it's a little more difficult, that. It's not as... for instance, they might switch it off for different reasons, not necessarily to block us. Some other conflict somewhere, somebody else disagrees and it's switched off. But we're affected. But at least we've got something to fall back on. That was the idea of it. Now, you could argue, would they have put in HF equipment now? Maybe not. I mean, this is quite a few years old, and they've stayed with it. Maybe now they might have a different idea and say not to do something different, but that's what they're using at the moment. HF comms. But as far as we're concerned as technicians, that's the lowest frequency we would need to be involved ourselves with. Most of our radio communication is line of sight communication, either at VHF, UHF, or microwave, SHF.
That's
Basically. Most of our communication is going to be that. So that's what we mean by polarization. And it becomes critical when we have line of sight communications, mainly. Now, I want to explain another type of... So that's our standard antenna. Now let's consider some variations on that. Some improvements, some changes on the standard dipole. The first change is perhaps the quarter wave. Now, I just told you that the most efficient is the half wave, didn't I?
Half efficient.
Well, what the theory of the quarter wave is quite sound, actually, and it was first used when radio was shortly after radio was first invented, actually, by a guy called Marconi. And if you remember, on our dipole, we connect our oscillator to the middle of two conductors, the total length of which has to be half a wavelength. Well, what Marconi found out was if he connects one end to only half of this, see, this half here is a quarter, isn't it? And this half's a quarter. So he connects this to a quarter wavelength, and he connects the other end to ground. Then, basically, he's got more or less the same characteristics as our dipole. It's called a quarter wavelength. Basically, you can think of the other half of the dipole as being in the ground itself. We've got capacitance between this half of the dipole and the ground, instead of the two halves of the dipole. This is almost as efficient, almost, not quite, but almost as efficient as the original dipole. It's called a quarter wave. One example of a quarter wave antenna would be if you're using VHF on a car and you mount an antenna. You should actually mount it on the roof for maximum efficiency, but let's just say, to make it look better, you put it here. Okay. Then instead of having this a half wavelength long, you could have it a quarter wavelength long, and where's the rest of the antenna is the car itself, or the ground. You see? Not quite as efficient as the dipole, but it would work, and you would connect your transmitter actually between the antenna and the ground of the car, the chassis. That's another use. Again, it is omnidirectional, radiation from all directions. Omnidirectional means literally including up and down, I mean everywhere. You need an omnidirectional antenna on a car, of course, obviously. And if you, for instance, had a communication system where you wanted to communicate from this building to your vehicles that are going to go around the city, then you want your antenna up here to be omnidirectional. Well, actually, you wouldn't want it quite omnidirectional. You don't want it transmitting up into the air. That's a waste. You want to communicate with vehicles, so you want to get rid of that. There is a way of doing that. I'll just explain here how we do that. If you have a mast you have what is called a stacked array. And the word array means a number of antennas connected together. Here we have an example of 1, 2, 3, 4 antennas connected together. They're all connected, although I've not shown it here, they're all connected to the same transmitter. Okay? Essentially, they're all dipoles. But the way they're connected in this so-called stacked array, in other words, on top of one another, is to make them so that they'll radiate in all directions around here, but the radiation up there is reduced, because it's wasted power. If you want to communicate with vehicles and cars and mobiles, we're not interested in wasting power transmitting up in the air, are we? We just want to go around down here. So this stacked array is used so that there is little radiated power, or I'll say no radiation.
The categorization,
Oh.
vehicle horizon, it's kind of
Sorry?
polarization or
Polarization?
yes.
The polarization is still vertical, yes, it is vertical polarization. The reason being, of course, that in a car, the receiver part of this, shall we say, its antenna is also straight up, isn't it? Vertical. You never see a car, or you shouldn't, with its antenna like that, because as it changes direction, it might miss the signal. This is always the best way to have your antenna for the car. So it's the same here. If you look on top of the roof here, I was going to suggest we can all go to the roof sometime, but it might be a bit dangerous. Don't want to lose anybody. We haven't got many left of you anyway, have we? So let's not lose anybody else. You'll be able to see these stacked arrays for our mobile communications. Okay. So basically, I've said here there's no radiation up there. Actually, there's a tiny little bit, but it's very, very small up there. It really radiates out.
Why don't you put 4 antennas back or on top of each other? There's no radiation going up.
In other words, how does this work?
Yeah.
Well, what actually happens is when we supply power to each of these from the same transmitter, the phase at which we supply the power changes between each of these dipoles. We don't supply it all with the same phase. The phase changes. The result is there's more radiation from the middle and less radiation going up. Now, it's difficult for me to explain that without the mathematics, but it's just that a stacked array like this produces that radiation pattern. And it's quite complex. These stacked arrays are worked out mathematically exactly how. You cannot just get 4 dipoles and connect them together. The way they're connected to the transmitter, we treat that as one solid antenna. We don't treat it as 4 individual dipoles.
We call that it is directional.
It is directional, yes. It is an example of a direction. But it's only directional in the sense that it's all the way around 360 degrees, but the radiation up, and indeed the radiation down to the ground, is minimum. So we don't waste power. To answer your question exactly how it works, it really is quite complex.
Direction for all sides except
Up and down, yes. If you were to draw a 3D model of the radiation from this antenna, you have to treat the whole thing as one antenna. Right? The radiation model looks a little bit like a large donut. This is the antenna in the middle here, and the donut is around like that. You know, you cut it in the middle. So that there's 0 radiation at the top and at the bottom, but maximum radiation out at the sides. Can you imagine, like, you know what a donut's like? As though we've just cut it in the middle here. But in fact, it's all the way around. Very difficult for me to draw, but there's some very good drawings in some of the books. I don't know if there's one in here that
So
demonstrates
we
it.
use antenna to keep the radiation down.
Yes, you would use this. So if ever you look around Jeddah, you might see a lot of this sort of stuff. Police transmitters, base station transmitters would be like this. Cellular radio transmitters, very often like this. Not all of them. Some of them are also go up as well, because a lot of people.
So use
Some of them circle like this.
Maybe that's a different type of antenna. Some of them are like this. Is that the type you're talking
Yes,
about?
yes,
Yes.
Folded.
Folded, what they call a folded dipole. Again, it's a little bit outside the scope of this course to go into exactly how that works, but it does the same job. It
So
is.
that's antenna good for repeater. No?
Is it?
Use a repeater. Use a antenna.
You use that sort of antenna, do you? A folded dipole. This type here. Folding means to go back on itself. Dipole. But they're all dipoles, these. They're all connected to the same transmitter, but the way it's connected is a complex phase difference. The distance between each dipole is also critical. The distance between each dipole is critical. It's got to be carefully measured. It's a dipole. Yeah, so it must be half a wavelength. Yeah, it's each one.
If in the car, dipole or car?
In the car, it could be a dipole or it could be a quarter wavelength. But it's a single element, all-round reception and transmission, of course, because the same antenna is used for transmitting and receiving, isn't it, in the car? So if you look on the roof of this building, you'll see many types of antenna, but you'll also notice this type. For the SMTS, they've got this type as well, for the VHF, haven't they? A Yagi.
Yankee.
Yagi.
Shaky, shaky.
A Yagi antenna. Probably one of the most popular antennas.
TV user.
TV. TV antenna. Yagi actually is the name of the guy who invented it. He's a Japanese guy, yes. A name like that must be Yagi. You must be Japanese. Mr. Yagi invented this. I'll explain in a minute how it works. You've probably seen this sort of antenna. You can buy them for your TVs. Usually they're UHF antennas, but they can be UHF, it can be any frequency, but UHF is very popular, this type of antenna. You can also get VHF versions as well. They'd be bigger, of course, because they're going to be lower.
Some antennas is VHF, UHF.
Yes, some are both, yes. A receiving antenna is not as critical as a transmitting antenna in its design. You can receive a TV signal just by putting a piece of wire out of the window if you want, you know, depending on how strong the signal is. It's not as critical. The efficiency comes in the transmitting antenna. That's got to be well designed.
Okay, Egypt TV.
Like Egypt TV, okay? But that's some distance away, isn't it? So you'll need a high antenna, I would think. Maybe a booster as well. I'm not sure where the closest transmitter for the Egypt TV is, but you would need a booster for that, I would think, or at least a high antenna. Pick it up. A Yagi. Now a Yagi is basically a dipole. This first thing here is a dipole. Now the question is, what are these things here? Well, what these things are, remember, okay, let's take our dipole. It's radiating electromagnetic energy, okay? Now let's say I put a conductor here in front of it. Just an ordinary length of conductor. All right? What's going to happen? Well, of course, the radiation from the dipole will induce electric currents in the conductor, won't it? Like a receiver. The electric currents flowing in the conductor will re-radiate energy. And if the conductor was a perfect conductor, you could argue that all the energy that was received by that conductor will be sent back again, will be re-radiated. Okay? So basically, each of these elements here, they're not connected to the transmitter. They're just what we call passive elements. Let me just explain that to you. All these elements here are what we call passive elements. Elements are parts of the aerial or parts of the antenna. Passive meaning there is no power connected to them. Now this element here, the dipole, is active because it actually has the transmitter connected to it. But these are passive.
And direct.
Well, I haven't mentioned direction yet. They're passive elements. Now we're going to see why we're using them and what advantage they have.
It's more gain. To get more
So
gain.
repeat the power.
Yes.
Repeat power.
Right, well, let me just explain
To sense something.
why we use it. They're acting like little transmitter receivers, aren't they? Well, what happens is this. In a correctly designed Yagi, first of all, let's assume this is a transmitter. It's easier to explain the operation of an antenna as a transmitter. Whatever you say about it, though, it'll work equally as a receiver. A good transmitter antenna will make a good receiving antenna. But it's designed so that each of these re-radiate the signal from the original dipole. But the distance between them is such that the re-radiation from these antennas, from these passive elements, I should say, in this direction, cancels the radiation from the main antenna, or from the main dipole. So, we have radiation from the dipole, remember, in all directions. But the re-radiation from our passive element, yeah, it causes it to be cancelled in that direction. For instance, a positive half cycle from the dipole, because of the gap between them, results in a negative half cycle from the first passive element. Well, these two cancel. So there's no radiation in this direction. But in this direction, they actually add. They enforce it. So what it's doing is getting the energy from our dipole and forcing the energy in one direction. In other words, this is a very good example of a directional antenna.
We can't say that the pathway direction is zero, because there is actually power to some.
Yes, it won't be quite zero. It's just in theory it will be zero.
Not in practical. You won't get a signal, but that doesn't mean that there is no any collapse of signal.
Well, don't forget, the way I've described it was...
yeah, but you're not taking the signals and direction, putting it in a new direction.
No, I know what you're saying. You're saying if I radiate from here and I radiate from here, okay, they'll cancel, but we are radiating. What I'm saying is, what I said here was a good way of explaining how it cancels, but in actual practice, because of the re-radiation from here, the original radiation from the dipole, right, will not be as big, or it'll almost be zero, not be as big as it was. That's what actually happens. There isn't any or very little radiation or decreased radiation in that direction.
Some antenna with reflector or reflection.
Some of them do, yes. These are what we call, if the elements, these passive elements, are placed in the front, and we call this the front because this is the main direction in which the energy is going to go, isn't it? So we call that the front of the antenna. We call these directors. These things are called directors because they direct the energy here.
Front direct
They're directors.
If we bring two batteries and put them opposite resistance, won't the batteries be consumed?
Not if you connect them like this, they won't. No, if you connect two batteries like this, no current will flow and no energy will come from the batteries. And that really is the theory we're talking about here, as far as the direction in this is concerned. Now, one way of showing this, right, is a polar diagram. I'm going to just put it here. I'll just erase this part a minute.
And the reflector is called active.
Not necessarily, no, it can be a passive, but if it's connected behind, it's a reflector, but I'll talk about that in a minute. Let me just... I'm going to put a fresh diagram on the board in a minute with all the information on it for the Yagi. This is sometimes called a polar diagram or a polar graph. What does polar mean?
Two.
Yes, it does. Or it can mean as pertaining to a pole. Now, if you remember in the Earth, we talk about the North and the South Pole.
Yes.
If you were to draw a polar map, for example, of the Earth, it would be a map looking at it from one of the poles, either the North Pole or the South Pole,
On the top of it.
either the top or the bottom. Normally, we draw the map looking at the side, because that's where most of the action is, but we could draw it either way. A polar diagram, you've got to imagine you're looking down on top of the antenna. And we draw a graph showing how much energy is radiated in different directions. And for a Yagi, if you were to draw such a graph, it would look a little bit like this. Okay? This is where your antenna is here. Now, there is a little bit of radiation in the back, but most of the power is going forward. Right? If I was to draw a polar diagram for the dipole by itself, the omnidirectional, it should be a perfect circle, shouldn't it?
Yes.
So that would be the omnidirectional dipole.
From the Yagi is not more distant than the...
Yes, well, we'll come to the advantages of the direction in a minute. This is omnidirectional dipole, but here the Yagi we can see is directional, isn't it? It's an example of a directional antenna. And in our case, the direction is this direction. And it has a lot of advantages. You get
top view.
Yes, it's a top view, exactly. Looking down on top of the antenna.
And
That's the way it's going to go.
for the Yagi, how is it like from the side view?
An interesting point. I think from the side view,
Would it be just like slightly-
if you looked at, strictly speaking, the best diagram is like a solid. It's like a three-dimensional diagram, like, you know, like that donut thing I showed you. I think the Yagi from a side view is something probably very similar to this, I would think. Maybe something like that. In other words, you have got up and down directionality as well, but again, most of it forward. An interesting point, I've never really considered a Yagi side view diagram, but something like that probably. The best sort of indicator would be a solid diagram. Anyway, we can see here that it certainly is directional in one direction. And the direction is where the elements narrow out. Now again, why are the elements getting smaller and what is the space between them? That has to be worked out.
Does increase the return of...
Yes, actually, the more of these elements you have, the better the gain. You can buy some elements, they have a lot of them, don't they? Many.
So we receive more little.
It'll be more directional, yes. Now, what's the advantage, do you think, of making an antenna directional?
Distance more than.
Well, you don't waste power, first of all. If you've got for example, a TV receiver, right, on the roof of your house, and you know your TV transmitter's over here, then there's no point in having your antenna receiving signals from everywhere else. You only want to receive it from the wrong place. So you can point it towards that. Yeah, so it's more efficient. Right, more efficient. That's the advantage of it.
You're right.
Yeah. For the advantage of directional, maybe on similar frequencies there's less chance of interference. And finally, a higher antenna gain. Now this last part you need some explanation of. I'll just put it down here. What we mean by antenna gain. I'll explain this part to you a little bit later. Just make a note of it for now. Very obvious once you know what we mean by a directional area. You would not use a Yagi for mobile communication because the word mobile means moving around. It's no use having an aerial just in one direction, is it? You need to cover.
Use it for TV at least.
TV is a very good example. Or if you've got point-to-point communication. If I just want to communicate with that guy over there, there's my transmitter, then fine. Work.
Is this wire telephone?
Sorry?
This wire telephone.
Telephone?
This wire telephone.
Wireless.
Wireless
Wireless.
telephone?
Wireless telephone. Some wireless telephone there is.
Yeah, but whenever you mention wireless telephone, I think of things like cellular phone or walkie-talkie or something like that. And that's mobile, isn't it?
No, it's small. This
Like
for home.
Uh-huh.
This,
Yeah, but that's mobile. You wouldn't use a Yagi.
not mobile. Distance maybe 100
Yeah, but you wouldn't use this type of antenna.
meter.
You wouldn't use this type of antenna for that, though.
Similar, like you can say short wave, it's directly to if you use it.
Wireless.
Similar, not say.
Are you talking about the antennas that we use for the high?
I'm talking about the antennas that work in the Yagi antenna.
So, you know, in theory, yes, we can have hundreds of elements and make it very, very narrow and tight and directional. But in practice, you wouldn't do that because you waste a lot of energy in the elements, you see. That's the problem.
About what the distance?
Range, it's line of sight. End of answer. Nothing to do with directional.
This one can use in transmitter and receiver.
Yes, that's right. We would use it in other
What is
transmitters.
question? What is?
He said, what about the range? Which means how far between transmitter and receiver. That's what you meant?
Yes.
Yes.
Just this.
Sorry about this.
He's very worried about that. He's so worried about it. But the answer's always the same. There's never any difference. It's basically line of sight. Now, power and you know, how directional your antenna is, the polarization, all this is to cut out interference in the case of a receiver and to stop wasted energy in the case of a transmitter. But in all cases, the actual range depends on whether you can see it or not. Right? If you put an antenna on top of one of those hills over there, I can see that hill. So I'll communicate. You could put an antenna down here in one of these streets. I can't communicate with you.
What about the board?
The range is only shorter than that, isn't it? But it's hidden behind buildings.
What about using low power or high power? What do you have?
Not a big difference. I'm not quite sure what power the microwave is. It's low power, isn't it? About. Does anybody know the figure?
That you're using also.
Not a big difference.
You put it behind this building.
Oh, yeah, I'm talking about, say, microwave or something like that. Not very much power involved. I'm trying to think what the microwave is. What power output is the microwave? It's in milliwatts. It's in milliwatts. And we're communicating between here and Ruiz, between here and Saudi City. But it's only a few milliwatts. Very small power. Very small.
The antenna of CNAV telephone, it's a dipole.
For which telephone?
CNAV.
The mole towards one end. It doesn't have to be in the middle. And depending where you feed it, all that changes is the impedance matched to the transmitter, that's all.
That's going to be the quarter or what?
It could have been a quarter wave, but I don't know really, because I'm not familiar with it. I'd have to look at the length and know the frequency, but...
Quarter no need to ground. Quarter
Quarter needs to be grounded, yes.
needs only.
Yeah, because you need a dipole, right? You're only using half a dipole, so the rest of it must be from the ground. The other side of your dipole is in the ground.
Quarter.
In the quarter, yes. In a dipole, you don't need the ground. Because it's not necessary. But I want everybody in this room, whether they do data or NCC, wherever they go, to have an idea about this. Right? So that's the reason why I've not gone into the technical details. But I will mention them and I will define them as I come. For instance, polarization, polar diagrams. You should need to know what that means. Everybody should need to know what it means. You should be able to know that a Yagi is directional, even if you forget why it's directional. Right? I explained a little bit of why it's directional, but even if you forget that, you should know it's directional, and would therefore not be used in an omnidirectional. Yes, if you remove these elements, it becomes omnidirectional. Yeah, exactly. So I've got to strike a balance here. I cannot teach this as though I'm teaching only radio guys. And at the same time, I cannot skip it because I think it's important for everybody to understand this. Yes, okay, then let's finish. Even compared to VHF. One disadvantage. So we we put up our big microwave antenna on our roof, and they do the same at Zealand. Yeah, and then all of a sudden, somebody builds a big building, directional aerial with higher gain, antenna gain, yes. And we measure gain in dBs. So until we've done dBs, you know, when we've done dBs, when we've covered that, then we'll go back to the subject of gain. Okay? But I won't do dBs until tomorrow morning, I think, because, you know, you need to be a little bit fresh, and we don't want to cover anything too technical just now. Okay. You remember it all. Okay, well, what is it, the part you want me to go through? We can begin any description of antennas by starting with our dipole. Now, a dipole, by definition, is a half wavelength, isn't it? Dipole. There's no such thing as a quarter wave dipole, right? There's only a half-wave dipole. And the only other thing you need to, a quarter-wave aerial, a quarter-wave antenna, is not a dipole.
It's another kind of...
It's a different type of antenna, but like a dipole, it is omnidirectional. That's what it's got in common with the dipole. A truly omnidirectional antenna radiates in all directions, up and down, left and right, all the way round, like a balloon, expanding bigger and bigger. In fact, we can draw a polar diagram which gives me half the story. It doesn't give me the full story. The polar diagram, looking at it from the, as it were, from the top of the dipole, from this end, it should be perfectly circular, you know, symmetrical like that. This is the polar diagram. So it doesn't matter which direction you are in from the antenna, you should get the same signal strength wherever you are. A lot of people get a little bit confused about what this diagram represents. They think this represents distance or range. And they think if they're within this distance from the aerial or from the antenna, they can receive the signal. But if they're that distance, they cannot. Doesn't mean that at all. Basically, if you imagine how they would make a polar diagram in practice, imagine they have a large area, like a large field, several acres, and they have a building in the middle of the field with the antenna on top of the roof of the building. Now, if this was a dipole antenna, they would then get into a truck or a car which would travel an even distance around there with an instrument that measures the signal strength, how strong the signal is, you know, as it moves around. Can you imagine that? Same distance away at all times, but moving around here. And then it plots this on a graph. Okay, this is where we go from, let's say from here, which is 0 degrees, all the way around to 360 degrees. Okay, from 0 to 360 degrees around the antenna. Now, if the graph is a perfectly straight line like that, that's right, meaning there is no change in how strong the signal is. It doesn't get stronger, doesn't get weaker, stays the same. Then, of course, if we plot that graph circular-wise on a polar diagram, what we call a polar diagram, which is basically a circular diagram, then this graph appears like this, because the distance from the center point to any point is always the same, isn't it? That's basically what it is. This graph is really the same as this graph, drawn differently, drawn in a circle rather than in a straight line, because we're actually drawing it from 0 to 360 degrees. But be careful with this indication. Don't get the idea that this represents distance or range. It does not. It just represents how strong the signal is. That's all. It doesn't mean to say that if you're here you don't receive the signal, if you're here you do receive the signal. It doesn't mean that at all. That's something different. Remember, the range depends on line of sight for most of our communications. For most of our communications, VHF, UHF and microwaves, SHF, they all rely on line of sight communications.
But here it is written the strength of the field inversely with the distance.
It does. As you get further and further away, okay, then the signal strength gets less and less, because you've only got so much power and it's radiating like a balloon, so obviously to fill that area it's got to get weaker and weaker, isn't it? That's the reason why in this example I said the car that travels around the antenna here must stay the same distance, so that we make the same comparison at all points. It's no use the car travelling like this, because it's close here and further away here. It's not going to make sense, you see. But that's true. The further away, the weaker the signal. But when somebody talks about the range, right? Yes. You know, when somebody talks about the range, we're saying, can you receive my signal or can you not? And a quick answer is, well, are you within, you know, visible sight? If you're not, probably you won't be able to receive the signal. Distance is not, you know, the fact that it does get weaker, yes, just make your receiver more sensitive. More gain in the receiver and you'll make up for that. So this is important about polar diagrams. Now, omnidirectional literally means in all directions, and in theory a dipole is omnidirectional. We also talked about a quarter wave antenna. This is where one side is grounded of our transmitter, for example, and the other side is connected only to a single conductor. That conductor need only be, if we were to measure the length of it, only be a quarter of the total wavelength, yeah, λ/4. Because it's assumed that the other quarter is actually reflected in the ground itself. So this will work. It's not quite as efficient as a full dipole, and it would be used for two reasons. One reason would be if your frequencies are much lower than VHF. Because the frequencies are lower, the wavelength will be much longer. So it might not be convenient to have a full dipole. Also, the other thing is, you might want to use a quarter wavelength on a vehicle. Even though it's not very long, you don't want too long an antenna on the vehicle, so you would use a quarter wavelength on the vehicle, on a car or something like that. This is quite efficient, but not as efficient as the dipole, and again, it's omnidirectional. It has that advantage. It would be omnidirectional. If you're using a lower frequency, it becomes maybe more convenient to use a quarter wave rather than half wave because of the length. And the other is, you might use it on a vehicle, on a car, because basically on a vehicle, if you imagine, I think I gave you the example here, it just means that if you say mounted here, sometimes you see this sort of arrangement. The length of the antenna itself might be a quarter wavelength, because if you had a full wavelength, even at VHF, it might be just a little bit too long, start waddling about. So a quarter wavelength might be used for that reason. Strictly speaking, you know, antennas a car antenna should really, ideally, be mounted on the roof.
But what always short in the tube, in the back of the car, and in the short one, the car.
Well, it depends on the frequency you're using, of course, don't forget, as to how long it's going to be. Ideally, it should be on the roof. But from a practical point of view, most antennas are mounted usually at the back for more convenience. But you know, whenever you radiate electromagnetic energy, if you have any metal close to the antenna, it's going to change the propagation of that antenna. In other words, although the antenna itself radiates in all directions, when it hits the car, you're going to get a little bit of reflection. And this is going to change the pattern a little bit. In other words, ideally it should be like this. But if you mount it at the back of the car, instead of getting a perfect circle, you might get something a little bit like this. Not quite perfect. It doesn't mean, say, you don't get any radiation in this direction, it's just a little bit less than you would normally get.
Stronger, the signal will be less.
So the most signal will be this way, because but then again, you could be next to a big truck, couldn't you? Which is also going to affect the radiation. Yeah.
The way you plotted the field.
Yes. On the polar diagram. Yes.
The second antenna was the Yogi antenna.
Oh, the antenna on the car.
No, Yagi antenna.
Oh, the Yagi. Okay.
Okay. They are different shape.
That's right. If we take a Yagi, what you have to do, of course, if we use the same principle.
Because in that principle, if you plot it from 0 to 360,
right,
and you cut the paper from the 0 and the 360, and you connect them, and look at it from the top,
I know what you mean.
Perfect circle.
Yes.
But if you do this, whatever you do in any other, the principle of drawing this
of the drawing. I'm speaking only about the principle.
The principle. In other words, what I said about the car going round the...
Yeah.
Okay. You can do the same. You can do the same. You could put a Yagi up here, for instance.
How would you transfer it
To a diagram, to a graph,
body,
polar diagram.
polar diagram?
Okay, well first of all, let's say we put a Yagi up in the middle of a field.
Okay.
And again, we've got our vehicle moving around with a receiver to receive the strength of this. But there'll have to be some point where we say, right, there's our 0 degree point, which is usually the point where you're pointing your antenna. And we say, okay, let's start here, and then we'll move our vehicle round. It should be clear that assuming the vehicle remains the same distance away at all times, just like we did with our polar, when it gets to this side, we should get a lower reading. Let's say it was a meter reading or something like that. The needle will go lower, indicating less strength here, and then it will increase again as it comes around here. Now, if we were to plot that on a diagram, it means at 0 it would be high, and then as he moves around, it starts to get less. Not quite 0. Doesn't mean to say we don't have any radiation backwards. We do a little bit, and then it would go high again.
Yes.
Now, if we take that and bend it round into a polar shape of graph, a polar diagram, then it would end up something like this.
It's supposed to end in a circle shape, not in this way. Because if you want to change this into a polar, you have to connect the 0 to the 360.
Yes, this is 0, 360. They're both the same amplitude. That should be the same amplitude as that.
Yeah, but it's like a strip of paper.
Yeah.
And you are just connecting it like this.
Not quite.
How are you changing?
It's a different axis. Here we're plotting 0 to 360 on a straight line,
Okay.
but here we're plotting 0 to 360 as an angle, not as a line, as an angle of rotation. That's the difference between the two. Like here, we say this is the 0 degrees. And now if we go by so many, say 45 degrees around, then we plot that as an angle of 45 degrees. Yes, and eventually we go to 90 degrees, that's an angle of 90 degrees here.
So there is no relationship between the two diagrams?
Not necessarily, you cannot just bend that round. But what I'm saying is, if we plot this as a polar diagram, then it should appear something like this. But we don't have a line as an axis, an axis, we have an angle, as an actual angle. The reason why we do that is this gives us a better idea of what's going on, you know, because basically that's what we're doing in our field, isn't it? We're going round the antenna. So it gives us a better idea of how it's actually behaving. And of course you've got to understand that even in this direction, we're still going to receive a signal.
Yeah.
But of course it's not going to be 0, it's going to be a little bit less than max. Whereas here, of course, we're going to get the best signal strength, the highest signal. That's really the difference between these two diagrams.
And we can say also that in this direction we can send to the much more farthest.
Well, no. Say, for example, we're using a Yagi, let's say this is our Yagi, and we're going to use it to transmit to somebody some distance away. But we're in line of sight. Yeah. Now the question is, we've got a Yagi, all right? This is our Yagi. Looks a little bit like this. When we point it, this is the end that we have to point for maximum. When we point it towards that guy, he'll receive a nice strong signal. When we turn it the other way, it doesn't mean to say he's not going to receive a signal. As long as he's there, it'll just go weaker. That's all.
Can't it reach to weak, so he can't hear it?
So weak he can't hear it?
Yeah.
In theory, no. In practice, maybe. But that depends on how direct. For a Yagi, I would say no. I think he would still be able to hear it, but it would be very weak. And the weaker the signal, the more it's going to be affected by noise. Remember, in any communication medium, whether you're talking about a cable or radio, you're going to get noise added to your signal at the receiver.
So there is no any loss of signal, whatever happens.
Oh, there's loss, yes. Yeah, but I mean, what I'm saying, what you're saying is, does he lose it altogether? What I'm saying is, maybe not. He probably won't. But he will get a much weaker signal. And therefore, it's going to be more affected by noise and perhaps interference. That's what I'm saying. It doesn't necessarily mean he loses the signal altogether. Not for a Yagi. Not for a Yagi area. Because although it is directional, there is still some radiation backwards and in other sides as well. So it doesn't necessarily lose it altogether. The reason why we make it directional is to improve the signal gain, what we call the gain of the antenna, and to make the signal to noise ratio higher by using directional. But it doesn't necessarily mean he loses altogether if you face it the other way.
That's what you mean about the advantage for directional antenna, which is the third one.
Yes, the higher gain, higher antenna gain. Yes. Now I'm going to bring back the subject of gain after we've done decibels. When we do decibels tomorrow morning, I'll reintroduce this subject of gain.
Are we ahead of schedule or?
Specialize entirely in it.
There are many types.
Yes, and designs of antenna. And basically, the only difference is the way they are directional or non-directional. The only other type I really need to talk about to you, which is probably quite a common type, is the dish antenna. When we've spoken about the dish antenna, that more or less finishes the subject of antennas. Okay? The dish antenna. First of all, where do we use a dish antenna? Well, a dish antenna is used primarily to give us the greatest or the highest directionality of the antenna. In other words, we get the greatest director antenna. If you want a directional antenna, nothing better than the dish antenna to give you this. Let's see how it works. Remember that if you consider, you've all seen a dish antenna, you know what it looks like, basically, right? Something like this. Mounted on some sort of structure. Okay, there are different sizes of dish, and we'll talk about why there are different sizes, etc. This is a dish antenna. And let's see how it works and what we're talking about. Mainly, we use dish antennas for what type of communication?
Radio communication.
Well, I'm talking about, when I say type of communication,
Radio
what sort of frequencies? Yeah.
High frequency. High frequency.
Microwave. 3 GHz.
Yeah, well, yeah.
SHF.
Yes, SHF. When you say high frequencies, be careful, or it could be interpreted as HF, which of course is not right. But I know what you mean. You mean higher frequencies rather than lower. SHF or microwaves are the ideal selection for this, isn't it? Okay. Now, what sort of wavelength are we talking about when we talk about microwaves? Talking about very short wavelengths, aren't we? Perhaps even 1 centimetre or so, or less, for microwaves. These very short wavelengths enable us to use quite small dishes. It is actually possible to use a dish for any type of transmission, any frequency, but the size of the dish must be much bigger than the wavelength.
If the wavelength gets bigger,
then the
dish
size of the dish
gets bigger.
get bigger, has to get bigger. The actual antenna in our dish antenna system, in a dish array, the actual radiator itself is a little thing here, a little dipole in fact, tiny little thing there. And depending on the type of system you have, you know, whether you're using this for, say, receiving TV signals or whether you're using it for a microwave link, whatever you're using, essentially you have a little radiator here. And that radiator radiates energy towards the dish. Now what happens when it reaches the dish? It induces small voltages and currents in the dish which re-radiates the energy out, like this. Now, in theory, it should be absolutely dead straight that it radiates it. In practice, it isn't. There's going to be a little bit of what they call divergence. But in theory, it would be nice for it to radiate straight out.
So that the radiator gives, you know, the dish first.
Hits the dish first. That's right. It actually radiates this way, towards the dish. And then the dish reflects it. Just like light waves. You know, if you had a torch, you've got a bulb, and you've got a reflector behind,
Yes.
which reflects it into a beam. Works exactly the same way.
But the beam is becoming bigger and bigger as much as you...
Indeed. Well, this one will as well. It's not absolutely. It does. There is what they call divergence. It will diverge slowly over the period. Now, if we were to have a look at the way the dish is made, it isn't exactly. If you were to look at a cross section of a dish, it's something like this, and you would have what they call the focal point of the dish.
Yeah.
Right, the focal point would be somewhere here, so many meters, or depending on the size we're using. That's where we would place the actual antenna.
It's like optical physics.
It's very similar. Because, don't forget, the higher the frequencies we're using, the closer to the light waves that we're getting. So we're going to start to treat our radio waves more like light waves, you know. And then this is where the antenna is, and then it radiates this way towards the reflector. And the reflector should reflect straight. Theoretically, it's supposed to be straight. In practice, it's not perfect. They will start to diverge a little bit. But it's quite straight. Now, if you think about that, I'll come back to the mechanics of it in a minute. There's a little bit to be said about the mechanics of all this. But if you think about it, if I was to draw a polar diagram of a dish antenna, what do you think it's going to look like? Yes, it's going to be quite. It should be quite narrow, shouldn't it? If this is the dot for the antenna, it should be quite narrow, like this.
Nothing behind.
In theory, nothing behind it. Yes, exactly. In actual, there is, but it's to do with the way it's made. To do with this guy here interfering with what's going on. There are also what they call side lobes. These are like this. A bit like one of these Swiss knives, you know, that you open up. These should be, however, these side lobes should be much shorter than the main lobe, and they, the problem with side lobes is to do with aligning microwave dishes. Let me just give you an example of this. We have microwave point-to-point communications from here to various places around, such as Oasis even, and Saudi City Airport. Those are the three main places. We've also got one just across here, haven't we? RB211, which is over there, isn't it? Yeah. Anyway, One of the problems with microwave communications is you have a microwave dish, all right? And remember what I said. In order to communicate with another guy, you've got to be able to see him, haven't you?
Yes.
All right? Well, that's one of the problems. But the other problem is you must make sure that your microwave dish is exactly aligned with the other microwave dish.
Yes.
Exactly aligned,
Yes.
right? Now, one of the problems that can happen when the technician is aligning these microwave dishes, and everybody in this room is going to be involved with this, whether you're data or radio or what, because microwave point-to-point is very important. One of the problems is this. I mean, you can imagine it, even a minute change in that angle, because of the distance involved, the number of kilometers, could move that beam way off target, couldn't it? And it's not unusual to tune your microwave and think, I've got everything aligned, but what in actual practice you're doing, you're running on one of these side lobes. What you've actually done, as you move this dish, it's a bit like moving this polar diagram around. And by moving the dish by a small amount, I'll exaggerate it a little bit, your main lobe is pointing up here somewhere, and what you've actually done is tuned your microwave onto a side lobe. And now, what you actually have got to do to align the dish, you've got to move your dish so that you get a certain signal here, then you should get a bigger signal as this one comes into play, and then even bigger signal, and then a smaller signal again on the next lobe. Do you see? So the idea is to move the dish, look very carefully at the signal string, because you're receiving a signal from the other side. So you look very carefully and find out which is the biggest signal string, the highest signal that you get. And that's your alignment. Of course, what makes it more difficult is this guy's got to do the same. So it does take a little bit of, over these distances we're talking about, it takes a little bit of, first of all, one guy will have to do it, and then the other guy has to do it, you know, to get his signal, and then this guy has to do it, and they have to keep repeating. And of course, the other thing is, it's not just up and down, it's also left and right. So it becomes quite a bit of a problem getting these dishes initially aligned.
For this side lobes, is it a cone shape?
Yes, actually it's, to be exact, if I was to try and draw a 3D diagram of that, it would be cone shaped. It would be, I'll try and draw this. Don't take this down just in case I'm wrong. This could be a side lobe. And then in the middle here you've got another cone, which is your main lobe. Does that make sense? Can you see what I'm trying to say there? It's like a three-dimensional thing.
For the side lobe, what's causing it?
Right, now let's go to what's causing it. The way I've described the action of a reflector here, it shouldn't have any side lobe, it should just have the main beam. But what actually causes this is the way we get the main beam out. Let me just go into a bit more detail of the mechanics of our dish. All dishes are going to be more or less the same, the way they work. All right, we've got a reflector. All right. And don't forget, we've got to have our little transmitter in front of the reflector, in front of it, here, so that it transmits towards the reflector, and then the reflector can radiate it. Well, there goes our problem. How do we put something in front of the reflector? Because if I put anything physical in front of that reflector, then the waves that are coming from the reflector are going to start bouncing off that thing that I've put in front of it. That's what causes the side lobes. And a good designed dish antenna should have very small side lobes. A badly designed dish antenna will have bigger side lobes. You can go into the market, into the souk, and buy a dish for you know, for, I don't know, they sell them for 80 reals.
How much?
80 reals.
80?
80.
80?
80. Now, do you think that's going to be a good one, or not very good? No. It might be okay for your TV reception, but it's not going to be, it's not, we would expect to pay more than 80 riyals if we wanted our microwave point to point, wouldn't we?
It's for receiver, not for transfer.
Yes, that's for a TV receiver, you see. But if we went to see, what's the microwave people's name? DMC, Digital Microwave Corporation in the States, which is what we've got, and bought this, a dish antenna for them, instead of 80, it'd probably be 8,000 or I don't know, 18,000 riyals or something for a dish, about the same size, or maybe even smaller. What's the difference? It's to do with the way it's made. It's going to be made better, and the side lobes are going to be less. The question is, there's 2 or 3 ways in which this antenna can be placed in front of the dish. One way...
Can you please repeat the point for why you will get on the side?
The side lobes, yes. I'm going to explain that with 2 or 3 examples. One way is to drill a hole in the back of the dish and put a metal rod through the hole. At the end of the metal rod we have our little antenna, okay, which then can radiate to the dish and the dish reflects it.
And can we say this antenna is RX?
It can be receiver or transmitter. In my explanation I assume a transmitter, but whatever I say about a transmitter, just the reverse will happen for the receiver in its simplest form. But you see what's going to happen? We haven't now got a perfect dish. We've got an imperfect dish because we've got a hole at the back here with this thing pushing through. So the other way of doing it, which you might well have seen, is to have the dish and then have another piece of metal coming up here in front of the dish with the antenna on it, which then radiates towards the dish. But again, this is not going to be perfect. And what happens is, the radiation from the dish outwards, some of it is going to hit this, yeah, and it's going to get reflected off, isn't it? And that's what gives you these strange side lobes. Actually, you get more than 2, you get several, but some of them are very, very small. That's what gives you the side lobes, because the radiation from the dish itself is going to bounce off this. And there's not a lot you can do. There is a design I have seen where this is your dish.
From the center.
Yeah, and they have, I'm not quite sure. Anyway, the little antenna, instead of being in the middle of the focal point here that we calculated, is a little bit off and radiates towards the dish this way. But even that's not very good because that doesn't give you a perfect pattern.
The angle also.
Yeah, the angles are a little bit wrong. But at least it's not in front of the main beam. It's out of the way. But it's not perfect. It's not going to give you a very good pattern then. So although there are different designs of the way in which they can align the reflector with the transmitter itself, or the transmitting antenna, then none of them are going to be perfect.
Not even using fiberglass?
No, not even. It doesn't have to be metal to affect a radio wave. Any
Metal also defect.
Yes, indeed it will, because any material that is not free space will either absorb or reflect a radio wave. It's to do with what we call impedance matching. When we talk about travelling waves and standing waves next week, this might become a little more clear as to why even a relative insulator can affect a radio wave. Not just conductors can propagation of the radio wave. Sorry, Fazal, you say?
Small dish we have seen.
Yes. Well, the size of the dish, that's something I haven't mentioned too much about yet. What do you think that depends on? Yes, it does depend on frequency, wavelength, that's right. The higher frequencies, shorter wavelength, we can use smaller dishes. But after saying that, in addition to that, you imagine you have a receiving antenna, receiving dish. Then generally speaking, if your dish is much bigger, the actual physical size of the dish is much bigger than the wavelength, then it'll work okay as a reflector. So let's say I have a dish which is, say, 100 times bigger than the wavelength of the signal that I want to receive. That'll work okay. But what if it's even bigger than that? No problem. So generally speaking, for a receiver, a receiving antenna, and to a certain extent for transmitter, but mainly for receiver, the bigger the dish, the better. Remember what's happening if we're receiving a signal from a satellite. I'm not talking about point-to-point necessarily here. I'm talking about satellite reception. Your satellite, this is the globe, your satellite has a certain footprint, doesn't it? Covers a certain area. So much power is radiated and it covers that area. Well, the bigger the dish we have, the more radiation we're going to trap.
And more satellite.
Right, and the stronger will be the signal that we get in our receiver.
The beam first goes to the dish, then
That's right. In the receiver, it's the opposite. In the receiver, it goes to the dish and then is reflected into the antenna itself. Yes, that's exactly right.
تقدر dish يكون received مرة satellite.
It gives you a better signal.
Sending
And generally speaking, with a bigger dish, strangely enough, it is more directional too. For instance, the main lobe of a small dish might be like this. Polar diagram I'm talking about. But the main lobe of a very large dish, big dish, might be like this. Notice it's narrower? More directional. This gives you a better signal. But of course it's more difficult to align. If you take one of these very big dishes, you know, several meters across, they usually need little electric motors to align them precisely. Mm.
With the digital, I think, digital system, no need for...
Yeah, well, on, let's say, the Orbit TV satellite,
Yes.
dish, you can get away with a dish about so big. Yeah, I've got one on my roof at home, and there is about that big.
Yes.
So it's not very big.
The dish, the reflector, isn't it supposed to just capture as much as possible of radio waves?
It is. It is meant to capture. That's why the bigger the better.
So it's like an amplifier.
Exactly. I'm glad you used that word. Remember, I used the word gain for an antenna, didn't I? I didn't explain exactly what I meant by that, but I did use that word. And that's exactly what a directional antenna does. It's like amplifying. And in the case of a dish, the bigger, the greater the gain.
Because
Yes, because you're taking more of the signal that's...
the way you explain how satellites emit its
Yes.
signal, it's like a big balloon, and it's like a grid at the end.
Yes, okay.
So whenever it hits, it's supposed to come back to the...
Yes, to the focal point, shall we say.
So it won't be coming as straight lines as you did.
It'll be converging.
Yeah.
Converging, yes, that's true. Think of that as concentrating the wave.
Like when you concentrate the light.
Like when you concentrate, like a magnifying glass.
A magnifying glass.
Exactly, like a magnifying glass, in a sense.
Yeah.
That's exactly what's happening.
Okay, after reflection, where that signal go?
On a transmitter, after it's been reflected,
Yeah.
it goes out,
To
well, eventually to the receiver.
receiver.
Yeah. Now, again, remember that we're talking about basically line of sight here, point to point, either to a satellite or to another ground station, but line of
No,
sight.
with the TV broadcast.
Right, well, with the TV,
Just
what you're
receiver.
talking about is a receiver, isn't it?
Just receiver.
Right, now a receiver is the opposite.
Yeah.
Receiver, you're receiving radiation from your satellite,
Yes.
hits the dish. The dish is like a mirror, but it's a concave mirror, so it's concentrating the beam to this point, the focal point.
The cable.
What's the
cable and TV.
Well, here you have what is, in satellite TV jargon, they call it an LMB.
LMB?
That's right. It's an antenna and also a frequency changer. And then that then goes down the cable to
No
your...
reflection with the...
LNB, it is
No reflection.
No, no. Well, it is. Sorry, yes, it is. It's reflecting from the dish to here.
To here.
Yeah. Now, if this was a transmitter, it's the opposite way round. The radiation comes from here down to the dish and then reflected out. But in a receiver, such as a TV receiver, it's the opposite. It goes that way, you see.
You thought it's the point.
The point, like the focal point.
Yeah, TX or
It can be a transmitter or receiver.
transmitter.
Hmm.
Tom said
ممكن يكون كذا وكذا.
think as it amplifier.
ممكن تستقبل
Okay, when the dish is bigger, you can bigger think as an amplifier.
الالمنت بتستقبل.
Well,
Or
can you... Yeah, can you ask me that again when I talk about gain tomorrow? Remember the word gain.
With transmitter and receiving both? Or
Both of them, yes, exactly. Both of them. You get gain in the transmitter and in the receiver, if they both use directional antennas, yes.
Can it be to use as receiver and transmitter at the same time?
You can, yeah. In fact, that's exactly what happens on our point-to-point communication using microwave. Using the same antenna, we can use it for transmitting and receiving.
Two position, this is the point. Two position, TX and take the...
Well, what I want you to think about here is using it just for one reason, either as a transmitter or as a receiver, not both. They can actually be used for both, but if it's used as a transmitter, that's right, exactly. If it's used as a receiver, it receives the radiation from the other side, wherever that is, goes to the reflector, and that concentrates the beam onto the actual antenna, shall we say, which is here. Yeah. The principles are quite straightforward. It should give us a very narrow beam, but because it's not perfect, we are going to get side lobes. They call them side lobes. And that can affect us if ever we're involved in aligning. Now, the reason why data guys are going to be involved with this as much as radio is because our microwave link handles telephone calls and data. All right? So the telephone and data people are very much involved with that microwave link. It's them that people come to if anything goes wrong, not the radio guys. It's the data guys. So they need to be able to handle this.
Wind can affect them.
Yes, indeed. In very bad weather, bad weather has two effects on it, but wind, if you take wind, if it gets very windy, it can move. And don't forget, you don't need much movement. A small change in the position of your antenna, just a small change, and it's gone, you lose it. It's gone off to a different direction, isn't it? So if you get very windy conditions, the antenna can move a little bit. So then you've got to be able to bring it back again to get it focused again onto the...
Can you repeat what's the side lobe?
The side lobe.
Why it is coming?
It's coming because we cannot have a perfect reflector. A perfect reflector would mean I can transmit from a point here to here, but this is in the space by itself with nothing connected to it. Well,
And not only that, this also will reflect something.
yes, that's right. Yes, even the point itself is going to interfere. Anything in front of that wave, anything that goes in front of that beam is going to cause small amounts of energy, if it's a transmitter, to be radiated in other directions. And that will produce a side lobe. Now, in actual practice, of course, we can't just have a point there with nothing on it. It's got to be physically connected to something. So we usually have some metal structure here to hold. In the case of, for instance, a TV receiver, we call it the LMB, don't we? And that's right in front of your dish. So you're going to have reflections off this structure.
When the size of the dish is bigger, the focus of the signals will
Yes, we get a narrower.
narrow focus.
Yeah.
Stronger for
The smaller the dish, the wider will be the.
stronger. Can the signal be stronger or only narrower?
I'm just going to make a quick list of what we've talked about. First of all, the first type of antenna we spoke about was the dipole. Then I mentioned the stacked array. Actually, there's another name for this, which I'll just have a look in here. There's two names for a stacked array. Just check here, make sure I've got it right. They call it something slightly different here. Antenna, collinear, what do they call it? Collinear array. They mean the same thing. And this is where you have a mast, and you have a number of antennas on top, like dipoles connected underneath one another like that. You remember that? Spoke about that? I'm not going to go into a lot of detail technically on how it works, but this is another type of array. Then we spoke of the Yagi, which we are more familiar with TVs. And if you look at it from a plan view, this looks a little bit like slightly different colour. We have a former there, and then
The quarter wave.
there, isn't it? And these are what we call what? They're directors, and they're passive elements.
If it is in front, it is good.
These are yes. If they're in front, they're directors.
If it is in back,
If they're in the back, they're called reflectors. Sometimes you might find another passive element at the back here, and that's called a reflector.
what function of reflector?
Sorry?
Function of reflector.
The function of a...
Reflection.
Well, basically the same function as the directors. You see, we want the wave to travel in one direction. So these direct the wave that way, but if I put an element at the back, anything at the back here, depending on the distance the element is, that will actually reflect in the same direction. That's the reason. The whole idea is to increase the gain of the antenna. These are passive elements.
Is another name for stack array? It is collinear.
Yes, that's right. I noticed in the book it's called a collinear array. It's the same thing. Yeah. So we'll use both words so you get familiar with them. You see, you can either have that or that. You see. This is the Yagi. Yes, I'll just mention the quarter wave, because that's another one we mentioned. Lambda over 4, let's see. Now, the quarter wave works in the same way as your dipole, except that one of the sides of the antenna is not needed because we use the ground. Right? So basically this would go to the input and the other input would go to ground. And this here is only a quarter wavelength long, isn't it? This part here, it's like half a dipole. Now, why do we do that? Well, it does save space if we're using lower wavelengths, because lower frequencies means longer wavelengths. So it saves space. And also, you might use this sort of arrangement on a car. It's more convenient to use this type of arrangement on a vehicle, perhaps, particularly at VHF.
What about this coil? What coil?
Yes, they're what they call loading coils. Basically, they change the characteristics of the antenna to match the particular transmitter or receiver that they have in the car.
Increase the dB.
It changes the.
Increase the dB also?
No, do you mean the aerial gain?
Yes.
No, it doesn't do anything to the gain. The gain is to do only with directivity, with direction. It doesn't do anything to the gain. It's matching, really, matching impedance.
Dish antenna.
Yes, before we do the next type, remember what the dipole is. It's omnidirectional. What do we mean by that? What do we mean by omnidirectional? In all directions, exactly. Even up and down. That's right. Now, of course, because it's all directions, it's not necessarily the best choice. Right? Sorry, what you're saying, Mohammed?
But
All directions. All, yes. Not old. Not all directions. Any direction is a new one. Yeah, all directions, even up and down. Now, of course, in most of our communications, we're not bothered about up and down. We want to go out and around. For mobile communications, for example, isn't it? That's where we would use this. So, this is where the stacked array comes in. In the stacked array, if this is your antenna, I'll just quickly draw it again here. Basically, the transmission from here is like this. Okay, all the way round. Yeah, you see, up is less, and here is less. So we save a little bit of energy, and that energy is now increasing our signal in the outward direction. Do you see what I mean? That's right, but it's all the way round horizontally. You've got to imagine this like a big tyre of a wheel, you know, that sort of a car.
You have to repeat, but why didn't use it like this?
Well, it could be convenience. You know, these dipoles, for example, and the equivalent of, have you ever heard of a whip antenna? A whip antenna. This is a quarter wavelength, and the reason why it calls a whip antenna because it's a flexible one. It blows in the wind, you know.
Yeah.
It's what's called a whip antenna.
This is the whip, no?
This one, and they're just very convenient and cheap.
Looks like one vibe on.
Yeah, just like one.
This is the quarter.
It's probably a quarter wave. Yes, a whip antenna would be, because it's fed at the end. So you've only got one element, as it were, and that would be an active element. This is active. This is active. This is active. These are passive.
But most use it. Quarter usage.
Yeah. Yeah, sometimes, you know, it's just a matter of convenience. A repeater, perhaps, just to save space and to be cheaper, etc., they use just an ordinary dipole or a whip antenna because it's...
But I think this antenna will give more space or more...
energy. Yes, this is more efficient for all-round coverage. And you'll notice the SMTS antenna system that we have here. First of all, what does the I'm asking the radio guys now, you might not know this. What does the SMTS, what the question I'm going to ask is, what is the frequency band of the SMTS? In what band of radio frequencies does it work at?
118?
Not the exact frequency, the band, just the band.
VHF?
VHF.
Because it
Yeah.
is interesting.
Yeah, it is VHF.
Because if the car even if the
That's right. The idea is the advantage of the VHF. What is the advantage of VHF? Abdullah? What advantage does VHF have over, say, UHF? Why is VHF better than UHF?
Cannot interference with another
No.
frequency.
No. What is the advantage of, you must know this. This is a very important question. What advantage would VHF have over UHF? That's one big advantage.
This is the main.
Yeah, really the only advantage. Mohammed, what do you think?
I think frequency not higher.
All right, the frequencies are lower than the, but is that an advantage? And if so, why? You must know this. Remember, we did cover these particular points, and these points are important for each band of frequencies. In our case, we're talking, isn't it?
Yes.
We're not just using radio because it's a fancy word. We're using it to actually get information between 2 points. Now, one point is line of sight communication. Okay, that's assuming you can see. You know, it might be a bad, hazy day, and you might not be able to see it, but that's not the point. The point is, assuming there were no interference, you could see it. Line of sight communication. And that applies generally to VHF, UHF, and also microwave. But VHF has an advantage over using UHF and over using microwave. VHF has one big advantage. Can you remember what that was? You should have it written down. They're all line of sight. All three of them are line of sight, but VHF is something different. Can you remember what it is?
Passing the building, which is less attenuation.
That's right. You must remember this. VHF signals can pass through buildings. Okay? Yeah, they pass through buildings.
Yes.
Go through the building. It will not.
Some.
Yeah, some of it will be attenuated, but a lot of it will pass through the building. That's why your radio broadcasts, you know, on the radio that you have in your car or at home, are VHF. Okay? So that you can receive the radio in a building. You don't have to go outside with your antenna every time you want to listen to the radio. In a car, you can receive it if you go under a bridge. So sometimes it gets a little bit, but usually you can receive it continuously when you go under bridges and things. That's the reason why they use VHF. Big advantage, and you must always remember this. But when you talk about UHF, it becomes a little more difficult to go through buildings.
The attenuation is more high.
Yes, that's right. It will penetrate buildings to a certain extent. I mean, you know, it's not absolutely stopped. Cellular telephones work at the high UHF band. Now, we can use cellular telephones in a building, of course, but anybody who uses a cellular telephone, it's better if they're closer to a window or closer to the outside of the building. If they go right in the middle of the building, it gets worse and worse, doesn't it, the signal that they receive?
There is more repeater.
Well, all the repeaters will be outside. They're not inside. Although some buildings...
The building or something like that.
Yeah. Although they do have repeaters in some buildings, like in the New York Stock Exchange and places like that, where people are using cellular phones a lot, they'll put a repeater in the room, you know, for the cellular telephone. But generally speaking, if your repeaters are outside, what they call the base station, on a roof somewhere, and you're inside a building, it gets it more and more difficult to receive the signal at that frequency, because it's UHF.
UHF more signal pass through building.
No. VHF, more signals will pass through the building. UHF, less signal will pass through the building. And then, of course, microwaves, forget it, that will never pass through a building. Now, somebody mentioned yesterday whether the building is metal or whether we're talking about plastic or concrete, or it doesn't matter. Any solid matter, doesn't matter whether it doesn't have to be metal. It can be plastic, it can be fiberglass, it can be concrete. Anything that's not the same dielectric as free space will reflect, and microwaves. Microwaves will not pass through. So microwaves are good for point-to-point communication, a much cheaper alternative than using cables. See? We'll talk a little bit more about that in a minute. You have to have line of sight. You've got to see the microwave dish. If you can't see the dish, forget it. You know, if you've got a dish the other side of this building, even if it's just across the road, forget it. You're not going to communicate from here. You've got to see it, right, all the way through. So, when you're talking about distance of communication, it's all line of sight. And the only difference the frequency makes, really, is on such things as attenuation, aerial gain, or antenna gain, noise factor, things like that, but not range. The range is not affected by.
You put glass like this
In front of the dish.
yeah,
There are certain materials that can be placed in front of a dish which will not affect the microwaves that much. For instance, a lot of microwave dishes are literally, they've got a cover on them, haven't they, to protect them from the weather.
Yes.
You notice this? Some discs, like a plastic, it's a special plastic actually, it's not ordinary plastic. There's your dish, just like a drum, and it's got a cover on it. You can't see the actual dish inside there.
The white plastic.
Yes, it's like a whitish plastic around it. But it's a special plastic, and it's only very thin, you know. And even then, it still takes a little bit of the signal away, not very much. But the reason for it, of course, is to protect it from the weather.
dust,
Sorry?
some dust inside.
Yeah, to stop dust and everything getting inside, and water if it's raining and things like that. That's okay, that's transparent to a certain, say with glass to a certain extent, but not much. I mean, if you try and shoot a microwave link through glass, a lot of attenuation takes place. Some of it will get through, but not much. Got to be careful, because glass, you know, normal glass has lead in it. Well, lead, of course, is a metal, isn't it? So you're not going to get very far with that.
So the HF band can pass through the building.
HF is no problem. HF, you talk about HF?
Yes.
Right, no problem.
As we go for low range, low band.
No problem at all. You go to the lower frequencies, like HF, MF, LF, it becomes easier and easier to pass through building. In fact, LF will actually pass into the ground or into the sea to a certain few meters, you know. Not very far, but it will go to a
What
certain extent.
frequency did you use for the dish here? Microwave?
It's all microwave in our case, yes. All SHF as far as we're concerned.
But the quarter leaflet is, you said web antenna.
This?
Yes.
Yeah, sometimes this is a whip antenna would be a quarter wave. I'm surprised you've not heard of the word a whip antenna before. Let me just put it down here then. Whip antenna.
About your HID,
Yes, single element sticking out, and it blows in the breeze of it. It's flexible.
this is what you use it for HF.
Yes, you can use it for VHF. Yeah. Yeah. Because the wavelength is about right, you can use that. But it's still quite long. You know, it's not a little thing. Okay, so, and then finally, of course, the dish was the other antenna we talked about. And various designs of dish, but essentially the dish antenna something like this. This is where the antenna itself radiates towards a reflector, isn't it? And then the reflector reflects it into a beam. And the receiver works the same way. When you're receiving a signal, hits the reflector, and the reflector points the beam or focuses the beam onto the antenna. There are different designs. If you look at a sort of dish antenna for a satellite receiver, sometimes they have like a couple of struts up here. It's not drawn very well here. Maybe 2 or 3 struts, actually 3 or 4 struts. And in the middle will be like an LNB, as they call it, burst frequency changer. Yeah, for the smaller ones. Well, it depends. I haven't mentioned anything about that, but basically, when we do a little bit more on the radio, you'll see what's happening here. We'll talk how an LNB works. If we generate the microwaves in a transmitter which is remote from the antenna, somewhere in the building, then those microwaves have to be taken up to the antenna by means of a waveguide. And a waveguide is like a pipe, a metal pipe, a hollow metal pipe. That's what we call a waveguide. So some types of microwave, don't forget a dish can be used at any frequency. If I wanted to use a dish at, say, medium frequencies, yes, but it's going to be a very, very big dish.
Yes.
Remember, the dish has got to be many wavelengths longer, bigger, than the frequency you're using. Now, medium frequencies, of course, you're talking about, say, 300 kilohertz to 3 megahertz, isn't it? Well, you work out the wavelength of that, you've got several hundreds of meters.
What about antennas?
Sorry?
Antenna which collect the signal.
Oh, you're talking about the receiving antenna for medium frequencies. They're called sniffers. They're not proper antennas. They're not as efficient. But because of the high power of medium frequency transmitters, they'll usually work. A receiving antenna is not as critical as a transmitting antenna. But theoretically, it's possible, certainly, to use dishes for any frequency. But of course, when we're talking about medium frequencies or high frequencies, the wavelength's so big, it's impractical to have an antenna like that.
Tell us that the dish, we have to take it as greatest direction antenna.
It is the highest directional antenna, yes.
It's not connected to microwave.
It's not just for microwave, but of course, in our use, it's microwave because of the size of the dish. We don't want it too big for that.
Because of the size of the dish, we use the microwave, but when we use lower frequency, it's better to use antenna.
That's right, it's better to use a different type of antenna. It's more practical. And not only that, don't forget, as you said, the dish is very directional. We don't necessarily want it directional. Sometimes we want it omnidirectional or close to omnidirectional because we want it for mobile work. So, you know, you've got to choose the antenna according to what you want. Yes, so if the microwave is generated remotely from the dish, it has to be connected to the dish. The microwaves themselves will be connected to the dish through what is known as a waveguide. Now, I'm going to just draw this down here as 2 examples. This is where we have a dish. And we have this waveguide, which is basically just a metal pipe, a hollow, empty metal pipe, specially designed. And this could be in a building, for instance. And this is where your actual transmitter is. This is where you generate your microwaves. Okay, so this is the transmitter which generates the microwaves. Then you have the waveguide. Guiding the waves, guiding the microwaves from the transmitter through up to the actual dish. Okay, this is called the horn. And then of course it radiates out to the dish and then the beam is produced. Okay, now after saying that, I'd like you to make a little drawing of this, but after saying that, in our communication system we don't use this method. We use a different method. The way we use it is we actually generate the microwaves here. Instead of generating them down here, because it's quite expensive to put this piping in, you know. It's
Near to the dish will be the generator.
yes, it'll be generated in front of the dish, so that it saves all this messing around here, you see, with because this is quite expensive installation. So for the sort of microwaves that we use a second way of doing it, where we still use the dish, but we actually generate the microwaves in front of the dish in a special box here. Right? And the same when we receive. Instead of receiving the microwaves and sending it down a waveguide, we receive them in the box here. Right? If you're talking about a TV receiver, this would be called an LMB, wouldn't it?
Yes.
And we don't send microwaves back down here, we send a much lower frequency. So this is the second way of doing it, where we actually have here the microwaves are generated here. Right? This is where the microwaves are generated. That's right. This is where the microwaves are generated, and all we have connected to the box here is a cable. This is just a cable carrying the signal that we want to send. Right. It'll also carry some DC power supply to
Or a
it.
TV broadcast?
It can be, yes, if you're using this as a TV receiver, right, like a dish antenna for receiving a satellite TV signal, this we call an LMB. And it receives the microwaves and then changes it to another type of signal, not a microwave signal, to go down the cable to your decoder.
So that the device offer sit down.
Step down frequency.
Step down.
Yes, that's right.
Yeah?
Technically, this is the first frequency change, yes.
Here, this first drawing. It's old or used.
It's not old. It's used in special installations, probably much high power. You would see this sort of installation at the airports. You see the big radar dishes that go around, the big dishes, you know, that scan the airport. That would use this sort of arrangement. Higher power. If you got high power, you would have it
Then we
remote.
can see here, we say here when you want to use a wave guide like this.
Waveguide.
Yes, waveguide we use high power.
High power and probably lower frequency, probably higher UHF, lower. You look at the size of those antennas at the airport, they're quite big, the ones that rotate. So you can tell just by looking at the size that the frequency is going to be lower than the SHF, lower frequencies than we use for satellite. That's radar actually, they're using radar.
That's sending signal and receiving.
That's right, they're sending and then receiving a signal, you see that.
Same signal.
The same sort of, you know, it's reflected off buildings and aircraft and anything in the airport, you see, so they can see what's going on. They probably use this sort of arrangement. But in Saudi, I can't think of any arrangement that we use that uses a waveguide.
High power.
This is basically high power and maybe lower frequencies, maybe the high UHF rather than the lower SHF. this might be, for instance, a wavelength of 10 centimeters. This might be a wavelength of 1 centimeter. You see the difference? Yeah. So this could be used for, say, radar. We can give an example here. Or higher power anyway. Now, we don't use this in Saudi, so there's no use me spending too much time on how waveguides work, but I'm just mentioning this because it is another way in which, you know, you can get energy to the reflector. Sometimes the actual microwaves are generated remotely and then they have to be guided with this waveguide, which is only a pipe, copper or some sort of metal pipe. Now the pipe can be round, or it can actually be, the waveguide can either be like this.
Maybe only military use this.
Military could use it. I've seen it on on ship. I used to work on on ships as a radio officer, and one of my jobs was to maintain the radar. And the radar on a ship sometimes used the waveguide system. Because the reason for that, though, is because if we put the electronics here on a ship, you know, a ship you get a lot of water from the sea, you know, seawater and the wind and the weather and everything, more likely to be damaged. Sorry? Aircraft have little dishes as well. I'm not quite sure with an aircraft where that's generated. Yeah. In front of the, yeah. I'm not quite sure whether that would use a waveguide. I don't know. I really wouldn't know about that, about the aircraft. But it's used on ships' radar systems. You would use a waveguide. I've also seen them where it generates it at the top as well.
Clouds, heavy clouds.
Yes. Well, actually, we're going to talk a little bit about weather and the effect it has on communication in a minute, but that's one way in which the system can work. But you will never be asked a question about this and waveguides, because we don't use it in Saudi. I'm just mentioning that so that if you ever see that somewhere else, you know what's going on. There's no difference in the way it works, really, between that and what we're using.
Also, we saw in airport one kind of antenna. It's called monopole. With the receive and the transmitting at the same time.
Was it a big antenna?
Yes.
Where was it used? In
Omnidirectional or Royal?
in Royal?
Oh, yes. Monopole.
A single pole. Monopole just means a single pole. Sounds like a dipole. Dipole antenna, I would think. Same thing. Or maybe even a whip antenna. Because this is very similar to the dipole. Not quite as efficient, because it depends on how good the ground is here.
The whip antenna the same.
But it's still omnidirectional.
The whip antenna?
Yes. Sometimes it's called a whip antenna.
The same dipole?
Yeah, this is a quarter wave.
Yes.
Dipole is half a wave, isn't it?
Yes.
But it's the same omnidirectional. It's still omnidirectional. See, this is half a wave, isn't it?
Yes.
This is just like a resume of what we did yesterday. This is also omnidirectional here.
Okay.
But the Yagi and the dish are directional.
One to one.
Usually, yes, that's exactly right. Because we wouldn't use these two for mobile, would we? You know? Basically, we've got two uses of radio, either point-to-point or mobile. This is the sort of antenna, or this, we would use for mobile.
The quarter antenna is a whip antenna.
It's an example of a quarter antenna. Sometimes they call it a whip antenna, yes. You might hear this word used. They mean a quarter. To wavelength. Transmitted wave should be received with a vertically polarized receiving antenna, right? if your wave is horizontal, then you should put your receiver horizontal to receive it. This is particularly true for VHF, UHF.
So that normal, not talking about the magnetic field.
It's always electric field direction that they're talking about, yes.
Electric field.
Mm.
But when you put it horizontal, you put the antenna like this.
Yes.
Like the big plug-in, it's here horizontal.
That one looks to me as though it's like that, isn't it?
Yes.
Right.
That's horizontal.
So you should have your receiving antenna the same. And if it's vertical, it would be like that.
Because the electric, which is used voltage in the
That's right.
so that we receive the signal.
You receive the signal, yeah. Now we all know that the magnetic field is always at right angles to the electric field. Doesn't matter which way round. But don't let that confuse you. Always think of polarization as being the direction of the electric field. Reminder, like since we're revising here, I'll also redraw those diagrams I had regarding the different bands that we use for local communication. VHF, UHF and microwaves. You know, I had notes on these some years ago and I've lost track of them. I'm sure some of my old students would have kept them, but anyway, here we go. If we have a look at VHF, okay, if this is the transmitter for the VHF, for example, and we have a building, then the wave from the VHF, which I'll draw like that, will pass through the building. Most of it will pass through the building. A little bit will be attenuated. Yes. In other words, only a small amount will be lost from the signal. So we can say here, if we wanted to put it in words, that most of the wave passes through the building. Okay, that's its big advantage of using VHF. Big advantage. In the case of, sorry, VHF, using VHF. Then in the case of UHF, take as our next example, the same setup exactly. We have a transmitter, we have a building. Now what happens, of course, not quite as good. Here the transmitter, same sort of arrangement, but here we're going to get more attenuation. And also some reflection. Actually, we also get a little reflection from the VHF as well, although it's relatively small. More reflection here. And what we have here, of course, is it passes through the building. And then finally, if we talk about microwaves, I'm just splitting it into 3 parts here. This is where we talk about SHF. Again, taking the same sort of arrangement, what do we get? Well, essentially, I'm going to say here nothing, most is reflected. If you remember just these 3 simple things, then that's the bottom line. That's really what we're talking about. The propagation and the way it behaves. It's easier to demonstrate with a transmitter what's happening. Needs a bigger antenna is one thing, and there's something else. Perhaps we don't mind having a slightly bigger antenna.
It's crowded with.
Yeah, you're talking about bandwidth now.
Yeah.
Yeah, don't forget. Always remember, you know what we've learned.
The bigger the bandwidth.
The bigger the bandwidth, or the bigger the band that we've available, the more room there is for everybody to use, right? And the more likely you'll be licensed for that frequency. VHF band will be overcrowded, and this is the case in most countries, by the way. You know, it's not just here or anywhere else. Anywhere, VHF is going to be the most prime. In the United States, if you wanted a little bit of bandwidth of VHF license, it'd cost you thousands, if not millions of dollars on a yearly basis. Because it's so, particularly in a place like New York or somewhere like that, because it's so. I mean, in New York, you know what New York is like with the big buildings all the way around.
Yeah.
You need VHF. UHF is useless for, you know, one. I'm not talking about cellular radio here. That's a different story. I'm talking about just mobile communications, private mobile communications. VHF is a very expensive option, but you don't have really much choice. Because remember, the VHF band goes from 30 to 300 megahertz. Well, that only gives me a couple of hundred megahertz or so to play with. And everybody has got to use some channels in there. And not only that, but because the wave goes through buildings, there's more likely you're going to interfere with one another if you're using the same frequency. Whereas at UHF, it's a little better. It's still not as good as VHF. We do get attenuation of the signal. If I have 2 buildings or 3 buildings here, then you probably lose your signal altogether. SHF, forget it. You can't. You're not going to use. This is no good at all to go through buildings. Yeah. Okay for point-to-point microwave, but useless for mobile communications. Just don't even consider it. Even though there's plenty of room in the band, but that's no good to us. And that's really the lessons what we need to remember here about which frequencies are going to be used for what. Now, you might have... The one big advantage of the SMTS was the fact that we're using VHF, and we've still got the licenses to do that.
Ask it, the question you ask, why you use VHF?
Yes.
Or UHF and CHF?
Right, why would you use VHF? What is the advantage? In a word, the word that they like to use here, you might have heard Richard using this word, is coverage.
The coverage you say.
Yes. Now, what do we mean by that? Somebody mentioned about range. What about the range of all these? Range means the greatest distance you can receive the signal. What can we say about all these? Basically, the range is the same for all of them. It's line of sight. The range isn't going to change. But what's going to change is what we call coverage. In other words, exactly if you can receive the signal or not depends on what's between you and your receiver. If there's a couple of buildings, then VHF will probably work. If there's maybe only one building or a low-level terrain, then this might work. If there's anything at all between you and your receiver here, it will not work. Anything. Even a bird flying in front of your antenna would momentarily destroy it.
What is the best coverage for V?
Yes, you can, in a word, VHF is the better coverage.
Because passing the...
Right. For example, we've got now a VHF transmitter, an antenna on our roof, and they say, okay, somebody got in a car and drove right out to the hills here and says, oh, we can receive it 60, 70 kilometers away. Great. But you couldn't receive it in the next street, you know. The point is, you've got to get coverage if you're in a city. So you've got to, I was talking about UHF, so you've got to really use VHF. Now the SMTS does use VHF, and that was its big advantage. Assuming the equipment worked. The frequencies were fine, as long as the equipment worked.
How will measure the distance?
You can, well, you calculate it theoretically. I mean, if you know the height of your antenna, and you know the height of the receiving antenna, you can calculate, according to the slope of the Earth, you can calculate what it should be. But what it actually is going to be depends on what you're going to choose as your frequency band and what's in between, you see. So, you know, basically I split it into three basic areas here, VHF, UHF and SHF, and we see the effect of any obstacle, which could be a building or a hill or a mountain, anything physical between us, and we can see the differences between. VHF is the best for coverage. We only get a little bit of reflection from buildings. UHF, we get more reflection and more attenuation as it goes through the buildings, meaning a lot of the energy in the wave would be lost as heat in the building, inducing electric currents into the structure of the building. And then finally, SHF, forget it. You're not going to get anything through the building there. If the question was something like, you know, you had to decide on a band of frequencies to be used for, let's say you had a fleet of vehicles, each one needed a radio so that you could keep constant touch with them. But they're only going around the city, they're not going to go outside the city, okay? And you had a central office where you had your transmitter and your base. It's a form of mobile communications. And you needed to be able to contact these vehicles at any time of the day, no matter where they were in the city. And basically, this is your ideal, isn't it, frequency band? Because being anywhere in the city, they're going to be hidden somewhere in streets, aren't they? Several streets away from where you are, with buildings between. So you're more likely to keep communication with this band of frequencies. If you didn't have that, your only other choice would be this. But I'll tell you now, you're going to lose them sometimes, for sure. Sometimes you'll get them, sometimes you won't. We've tried this driving down Medina Road using the trunking radio, which runs on UHF. Comes in and goes out. As he drives down the road, sometimes you receive him, sometimes you don't. Changes depending on what he's passing at the time. This, of course, forget it. You would never use this for mobile radios. Unless it's satellite, right? But that's a special case.
Point to point.
Yes. Normally this is, what you would use this for is, instead of using cabling, you would use a direct point-to-point microwave link, what they call a microwave link. Satellite's a special case. Finally, the other type of antenna is the dish, which we would use at SHF because we want to make it as directional as possible. I mentioned briefly this morning there are two ways. This way is where we generate the microwaves remotely, and in order to get that signal up to the dish you have to use what is called a waveguide, which is basically a metal tube or metal guide, quite an expensive arrangement, usually used for high power or maybe radar installations. The most common arrangement for communications is this, where the microwaves are generated in front of the dish. They're actually generated here. They're not generated remotely. So you have